All right. Seems like we have lots of people today. Thank you so much for coming. So I'm Long Chen. I'm a research scientist at Wave. Firstly, I'm going to give an introduction of this tutorial about our motivation and its schedule. So our title is End-to-End Autonomy, a new era of self-driving. So our motivation is that last year we saw that both industry and academia are shifting towards end-to-end solution. Especially one milestone is Tesla SFD beta V12, claiming that they're using a single end-to-end neural network to train their driving model. And another milestone is the Uni-80 paper, won the CVPR best paper. And here's also a very good survey paper about the end-to-end autonomous driving paper, if you would like to have a look. So for today's schedule, we really want to give us like an amazing tutorial about end-to-end driving. So we have lots of sessions today. So firstly, we will have a foundational session. So we have Jamie Shelton, the chief scientist from Wave. We'll talk about the role to embodied AI, some practical experience from the industrial. And from the academia, we also have Hong Yang Li, assistant professor from Hong Kong University and research scientist at the Open Drive Lab. We'll talk about some critical points about the foundation models to solve end-to-end autonomy. We will have a 20 minutes coffee break in between. The next session is a deep dive sessions with our scientists at Wave, talking about lots of hands-on experience. Nikhil will talk about the neural simulator, and Gianluca will talk about the world model. And we will have another coffee break for 15 minutes. And then lastly, Oleg will talk about the language meet driving. So lastly, we have Alahi, the head of research AI at Wave. We'll talk about some of the future direction of end-to-end autonomous driving. So without further ado, please allow me to introduce our first speaker, Jamie Shelton. Jamie is a chief scientist at Wave, leading the science group building foundational model for embodied AI to enable safe and adaptable autonomous vehicle. Prior to this, he was a partner director of science at Microsoft and head of mixed reality AI labs, where he shaped foundational features such as body tracking and hand and eye tracking that enables Kinect and HoloLens 2. Let's welcome Jimmy.
Okay, fantastic. Well, thank you all for joining. It's amazing to see such a full room, and excited. We're all excited to be here to talk to you today. I'm going to give you a little bit of a sort of overview of this space that hopefully will point the direction for some of the talks that are coming later on, set the scene, and inspire you by the opportunities ahead in the space of end-to-end autonomous driving and the applications of that towards embodied AI more generally. So you can't have failed to see the accelerating progress in AI over the last few decades. Breakthrough after breakthrough, covering all sorts of domains, from handwriting, language, speech, computer vision, of course, have been falling year after year at an accelerating pace. And I thoroughly believe that driving is next on this list. But driving is really challenging. You're out there in the real world, surrounded by safety critical scenarios. Here is just one image from the streets of London that we drive every day. This is not an edge case. This is a very normal occurrence. Your system that you build has to be able to deal with that. And the complexity of the real world, the challenges, the variability, and the fact that there are humans, very unpredictable humans, that populate that environment. But if we can unlock the potential here for AI to come out of the cognitive domain, the chat GPT domain, the generative AI domain, and actually embody that in the real world, the opportunities are immense. And of course, we've all seen these kind of examples from science fiction over the years. But we're really on the cusp of that science fiction becoming reality, a reality for us in our day-to-day lives. And I think, as we'll see in this talk, I hope, driving is probably the first place this is going to really mature into mainstream use for everyday life across the planet. Now, looking back at the last 10, 15 years, maybe, there's been a clear trend from major advances around the sort of ImageNet dataset and AlexNet on top of that, and everything that's come from there in the space of the computer vision community here, of course, leading rapidly on to the amazing advances in NLP with the advent of transformers and the incredible capabilities of next token prediction in terms of language and other forms of generation that we've seen. And really, the next frontier is going to be taking these advances and putting them out in the real world, the open world, the unconstrained, unstructured complexity of that, where safety is paramount. So just to give you another example of the kinds of environments that we are operating in every day, in London, here is again, not an edge case. This is a pretty normal thing, very complex environment with roadworks here. You've got passing traffic. We've got to negotiate out into complex traffic that is, again, very unpredictable, navigate through this. And we're able to do this all without HD maps and just pure end-to-end intelligence. So, what's the difference? What is end-to-end and why is it different? So if we look back to a more traditional autonomous vehicle stack, it looks a little bit like this. So you've got some sensors. Typically, it's a case of throw as many sensors as you can at it because they all, of course, add value in some sense. Pass that into a set of perception algorithms, computer vision algorithms, detecting bounding boxes, lanes, objects, etc. Simultaneously try and localize yourself to a map, often a very high definition map that you've scanned in great detail. And then pass that on to a planning system that sort of predicts what's going to happen next with the other actors in the world, and then a policy that decides how to act given all of that information. And pass that on to a control system that finally actuates it. Now, this can work, right? There are fantastic proof points of this in the world. It does work, but it comes with a very high cost, and nobody has yet done this in a way that is really a sustainable business at scale. And it's very, very challenging to scale for a number of reasons. The perception stack, you have to supervise it, you have to label a lot of data. That's expensive. Furthermore, as a human driver, imagine you could get into a vehicle and put on the world's perfect head-mounted display that turned your camera sensors, your eyes, into a perception. So just visualize the bounding boxes that you get from the perception algorithms and everything else, right? Would you be comfortable to drive from that, not being able to see the real world? I wouldn't. That's a nice thought experiment that I think motivates the fact that you're throwing away stuff, right? You don't know exactly what it is, but you're throwing away stuff. It's an information bottleneck. Next, of course, right, this diagram up the top is quite complex. There's quite a lot of boxes there, and the interplay between them is non-obvious. So even if each individual one you can manage and understand quite well, this is a big complicated system. Those maps, they're also expensive to build. And the more sensors you throw at this problem, the more compute you need, the harder it is to integrate into a vehicle, etc. So instead, what we've been pioneering at Wave for the last 7-8 years now is really an end-to-end system, and it looks a lot simpler. So Similar kind of sensors on the left, although we're very flexible with what sensors we use. Genuinely an end-to-end neural network, pixels in on one side and driving trajectories out of the other side, and then a control system on top of that. And this has, really many advantages in addition to the overcoming the problems that I talked about a moment ago with the traditional stack. It comes with benefits like it's computationally homogeneous, very easy to deploy to different silicon on the vehicles. We can generalize through data, and we've been doing this the last couple of years as we've been taking what was able to drive just in London on just one vehicle to driving on many vehicles across the UK and now across the US and other places as well. And that all happens through data. It's pretty scalable and an economic solution to this. You can use just cameras if you want to. If you want to throw in other sensors, you can. And we don't need those high definition maps as well. And it ultimately it works, and it works better. The performance and safety of this outperforms what we've seen from hand-coded solutions. So here's a few interesting examples of the kind of emergent generalization you get when you put this on the road. So, this top left example, it's learned to pull out of the way, and it could see that vehicle coming. And these are, again, typical narrow streets in London where you've got to negotiate with users. It learns that there's someone coming, there's a gap, let's pull in there, wait for them, and then pull out. Not something we've programmed, something that it learned. Similar example here where it sees that this van is indicating to pull out, and perhaps too politely pulls back and lets it turn around. A slightly more unusual case in the bottom left here with this car that's decided to reverse up the road and find a parking spot. But again, effortlessly handled with ease. And maybe a more mundane example there on the bottom right, but just some clutter on the road. And again, we didn't have to program any of that in. It sort of learns that clutter is to be avoided, so avoid it. We've been working, as I mentioned, on generalizing the driving across different vehicles. We now have it integrated into about 6 different vehicle types. And this little video on the right is the same neural network driving 2 very different vehicle platforms, one following the other as they drive around the streets of London. So I'm going to spend the majority of the time today talking about these 3 topics, which I think are at the frontier of embodied AI research: simulation, multimodality, and foundation models. And again, this will hopefully be a very brief introduction to some of these areas that you'll see more about in the talks that follow the rest of the afternoon. So without further ado, let's dive into simulation. And of course, if you're doing end-to-end driving, well, there's no obvious way to sort of simulate bits of it. You have to simulate the whole thing. Now that comes with challenges, but it also comes with opportunities. And I'm going to show you some of the latest work that we've been doing on end-to-end simulation. So here's a few, of the various simulators out there already today. Lots of fantastic work from across the community and across the industry. And they all kind of, in a sense, do different things, right? They all attack the problem slightly differently from different perspectives and with different requirements. And that's perfectly reasonable. What I think is, really important for a simulator are these things on the left here, right? You've got to close the gap. It's not just a visual perception problem, as we've said, it's a behavioral problem. So, you can't just have photorealism, you have to have behavioral realism in your simulator. The world is complex. It's not just a bunch of rigid bounding boxes moving around in a scene graph relative to a static world. The world's more complicated that you have pedestrians, you have cyclists, deformable objects. The lighting is incredibly challenging often. The textures of those objects change, the brake lights, the wipers, the indicators, the traffic lights. It's a really rich world out there. And a lot of the, it's very easy to make seemingly naive, seemingly okay assumptions, but then they really limit you in terms of what you can reconstruct. You've of course got to not just simulate the visual side of things, but the whole interaction, the whole robot, interacting with the world. It's got to be scalable, and ultimately scalable really most of the time implies data-driven. And last but not least, you need some control over this. You need to be able to, especially around the long tail, simulate important safety critical scenarios. And I think we're getting there. So we'll talk a little bit about some of the work we've been doing at Wave that is ticking a lot of these boxes. So we've taken the approach of resimulating the world, so capturing the world from real cameras, as you see in the top left, and then turning that into some form of simulation, resimulation of that scene. And it's been amazing to watch the progress in neural rendering over the last few years that have enabled us to even imagine doing this kind of thing. On top of that sort of reconstruction technology, we've got to turn it into a simulator. And so what we've been building is something called GhostGem, which just turns this into a full closed loop simulator. So you take actions, the driving model takes actions in the simulator that updates the state. You get a new set of images coming back in, and you turn that loop, and you see what happens. Here's a few examples of the kinds of scenes that you can reconstruct there on the right. But what I'm really excited to talk to you about today is something we just launched yesterday, so sort of really hot off the press, which is Prism One. And again, this really comes back to the critical importance of simulating dynamic and deformable actors in the scene. They're the most vulnerable road users in many respects, and yet so easy to just sort of gloss over because they're hard to simulate. So Prism is a self-supervised 4D non-parametric scene representation that essentially just tries to reconstruct everything it sees over time and give us some control over that. So a couple of examples here in London and the Bay Area. But it's when you get scenes like this with these cyclists and the pedestrians and the complex reflections of the puddles on the water that Prism starts to really come into its own. It's able to actually reconstruct those pedestrians as they're pedaling, and it's not just some kind of rigid cartoonish cyclist or pedestrian that you're seeing here. Oops. Here's another example where we're deliberately now perturbing the camera path with this sinusoid to show we've got that level of control here. This is a simulator, and I mean some really remarkable things here. I think first of all the fact that we're getting this pedestrian at all with their umbrella, and then all of the complex lighting and reflections off the water on the road there. Furthermore, the traffic light you see up there changes color as part of this simulation. Here's another example where we're doing some more new view synthesis. It pauses here and pans to the left and right. And again, it's really important to be able to do this, because if you've got a closed loop simulator, it's going to drift off the path that you drove originally. And so it's important to be able to see what, to let that simulator play out. In these examples, instead of letting the car keep driving, we've sort of frozen the camera, and we're moving time backwards and forwards. So you can see that the dynamic objects in the scene are they're moving. We're able to reconstruct those in beautiful accuracy. And furthermore, again, things like the traffic lights, which would be hard to approach in other ways. And a couple more examples here with challenging lighting conditions, reflections on the road, the glint in the building up there. Subtle things but they do matter when it comes to testing the driving models that you're building to a level of fidelity that you need. Now, as part of developing Prism, we have also been, of course, using an internal data set to benchmark this and to track progress. And we're delighted to also share this data set. It's called Wave Scenes 101. You can download it from our website. And this is designed specifically to help the community to focus on this problem of 4D scene reconstruction. It's super important. I'm sure there are, you all have amazing ideas in the audience here of how to improve this even further. And we hope to sort of empower and excite you to do that. It's got, a variety of scenes, different countries, different road types, weather layouts, weather lighting conditions, lots of cyclists and pedestrians. And we've even specified a held out camera so we can test new view synthesis in this particular, a nice way. Hit just 3 examples, relatively simple ones in these cases, but showing the variety of different lighting conditions we've got here, from sunny to rainy to dark. But perhaps more interestingly, we've got some really, really challenging scenes in here. So this top one harks back to the first slide in the talk with all these pedestrians crossing the road. And again, a true simulator for solving autonomous driving is going to have to deal with these kind of situations. But of course, you want to go beyond just resimulating exactly what happened, and to be able to create new things as well. Here, both, we can combine the neural rendering and generative AI to start to bring this up and simulate these rarer edge cases. So this time last year, we launched Gaia, which is a generative AI for autonomy, a generative world model. And essentially what that means is you can predict you can generate videos, but you can controllably generate videos. So you can action condition it on what can come next, or indeed language condition it to tell it, what the weather should be like, or what objects should be present. And this is architecturally a fairly straightforward next token prediction plus some video diffusion on the end. But as you'll see, as you'll see in a second, came with some really amazing results. Of course, this has become a really exciting and crowded field over the last couple of years now, and delighted to see further progress in this space in the years to come. But here's a few examples of Gaia just being left to its own devices. Just let it generate. Don't try and control it or anything. And I think the beautiful thing about this is these are long form videos. It's generating these for long periods at a time. It's generating a variety of different road layouts, conditions. It's able to deal with the dynamic agents. It's got some clear sort of mental representation of dynamic agents versus the static scene. And they're certainly not perfect, and there's rough edges around them, but on the whole, it looks pretty convincing. You can do some nice things with this, and one of my favorite is producing diverse futures. So you give it the same starting point, and then you let it, diverge. And so in this example, on the left, the white car in its imagination has reversed and let us pass, but the white car on the right has decided to pull forward, and we then give way as the ego vehicle. We can also control it, though, and this is where it starts to get back to simulation. How do we, start to close the loop here? And in this example, we deliberately steer the ego vehicle towards the oncoming traffic, and lo and behold, Gaia imagines that this oncoming traffic swerves out of the way to avoid us. More recently, we've been looking at how to use Gaia to add objects and join the dots between what we saw with Ghost Gym and Prism and what we've just seen with Gaia. And in particular, one thing that's looking really exciting and promising is the idea of just adding objects realistically. So here we're taking a reconstructed scene from Prism and drawing this cuboid of where we want a vehicle to be, and then letting Gaia fill it in. And lo and behold, a car appears with realistic lighting, realistic shadows, etc. A couple more examples of a bus and 2 more cars here. And then here's a video example where all of the dynamic agents here now are being in-painted by Gaia as it goes. And there's some really interesting, remarkable stuff, especially around the fact that there's this is multi-view generation, and we're able to, accurately infill this object in both cameras simultaneously. And then, back to Prism, I think, another really interesting topic here is counterfactual simulation. So taking something that really happened and then changing it in some way. So here we're taking this pedestrian, removing that pedestrian, and then, you can compare A versus B, what your driving model does in these situations. And this is a really, really clean, clear, and I think causal demonstration, therefore, of what matters to that driving model. So I expect to see much more around counterfactual simulation in the months to come. Okay, moving on, then the next topic I wanted to touch on briefly is multimodality. And really, this is all about language, and language meets driving, which sounded completely crazy when we started this a couple of years ago, but I think hopefully probably does not sound quite so crazy anymore. Opening up all sorts of applications from explainability to the, improving the raw intelligence of the driving, and building trust and safety around autonomous driving. And there are so many exciting applications here, but the first one I want to talk about is Lingo 1, which was a grounded visual question answering model that we put out a few months ago. And here, relatively simple architecture again, put in a snippet of your video into some encoders, into a large language model that's been fine-tuned, and then turn that into a dialogue loop. And we sort of explored this in two modes, one just generating commentary, as you see on the left. So here we're driving along, it's saying, I'm maintaining my speed. I'm slowing down due to a jaywalker. I'm slowing down in preparation for the upcoming left turn. And on the right, you've got a true VQA system where you can ask what it's seeing, and it will describe that, and you can keep, you can keep refining and asking more questions as to what's going on in the scene. We extended that with Lingo Show and Tell, which now you can ask it things like, what are you paying attention to? And not only will it tell you, but it will also, draw with sort of a semantic segmentation type output overlaying onto the video to really sort of connect what it's seeing with what it's saying. But more recently, we've started to extend Lingo and released Lingo 2, which is all about not just commentary and explainability, but actually driving at the same time. So I believe this was the first language and driving model that went out on public roads, actually controlling the vehicle as well as being able to explain its actions. And so a few examples here: accelerating, increasing speed, making a right turn to stay on the route, reducing my speed for the upcoming turn, turning right to follow the route, etc. And this is the same model that is producing the text is also actually the policy and producing the driving commands here. Keeping left to follow the route, turning left to follow the route. Another example: reducing speed for a turn, turning right to stay on the planned route, increasing speed limit to meet the speed limit, reducing speed due to jaywalkers, moving past a parked vehicle. Keeping speed, the road ahead is clear. The zebra crossing is clear. Keeping speed, the road is clear. We can also now join the dots between the language models that are driving that we just saw with Lingo 2 and the simulation technology, and use simulation to explore controlling the driving system with language. And so in this example, we've got a simulated environment where we ask it to stop behind the bus on the left and instead to overtake the bus on the right. And lo and behold, this language-based prompting changes what happens with the driving, as you'd expect. And I think the next thing here is back to those counterfactuals, changing things. So here we're taking an original video and using Gaia to insert these vehicles. So that's the only thing we change. And then we look at both how does the driving plan change? And that's those sort of wiggly lines that are probably a bit hard to see on the slide, but also how the text change. And so on the top left, it says increasing speed to match the speed limit. On the bottom left, it says slowing down to match the lead vehicle's speed. And on the right, stopping due to the red light and stopping behind the stationary traffic. So again, it's this, you change one thing in the scene and you explore what happens. And if you can do that successfully over a statistical sample, you're getting some really good confidence about what's going on in the brain of these models. The final thing I wanted to touch on today is around foundation models for embodied AI. Now, a foundation model, as we've all heard the term bandied about, but I think this is a pretty decent definition. It's a model that's trained on a diverse set of data that can be adapted to a wide range of downstream tasks. And of course, huge progress in the community on this the last few years, certainly starting with language and then language and vision coming together. Major advances on this slide, of course. More recently, in the space of embodied AI, this has also been garnering attention. And sort of my favorites are these ones at the bottom, and especially the ones where you're starting to see cross-embodiment results, where you can train across multiple different robotic embodiments jointly and get better policies for each of those embodiments than had you trained specifically for that embodiment on its own. I think that's an amazing result. And I think really points to the future here, where we can start to learn from from vehicles and from humanoid robots and any other kind of robotic embodiment, and take the data and learnings from all of those and combine those together into something that's bigger than the individual parts of this. Now, when it comes to foundation models in embodied AI, there are some genuine hard challenges that are distinct from the more traditional cognitive AI foundation models we've seen so far. Data being perhaps the primary one here. The data just doesn't exist on the web, right? It's not like you can go and scrape crawl the web's web pages for text, or crawl YouTube or equivalent for videos. It's not there. So you have to find it somewhere. Now, turns out in autonomous driving, that's relatively straightforward compared to some other forms of environment. You've got all of these cars now, almost all modern cars are equipped with loads of cameras. There's dash cameras out there, etc. So I think autonomous driving is where you can actually solve this. But it is going to be challenging nonetheless. Once you've got all that data, of course, that's a lot of data and you've got to process it. And that leads to huge compute demands for training. And finally, you've got to deploy this on a robot of some description. And robots, as you may know, if you've worked with them, don't always do what you ask them to do. You've got the challenge of distilling a big foundation model down onto something that can run at low latency on an embedded chip. You've got that highly ambiguous, uncontrolled operating environment you've got to work in. And of course, you've got to deal with the safety and validation of this. But as I say, in the space of driving, I think we can make some real progress here. You can get internet scale video data. You can get a subset of that that's slightly smaller, which is more around embodied video. You can get large-scale driving data from deployments of existing vehicles around the world. And then you don't need much on top of that. The icing on the cake is high-quality driving data that you actually learn a policy from. And, I think it's really interesting to look at, this kind of diverse sources of data and question, is it useful? Is this useful? And I think the answer is yes. I think, each of these videos has something interesting to tell us about the world, how the world works, how humans work, how physics works. And so I do think that there's a lot of value to be had by learning from a very diverse set of video data and other forms of data to help us even if all we care about at the end of the day is the driving task. And so ultimately, I think these multimodal foundation models are going to help us unlock safe and generalizable autonomous driving, and hopefully much more beyond. So to wrap up today, thank you for joining us for this tutorial. I do think embodied AI is the next frontier in AI, and that self-driving is the way to get there first, to show the value to the world of embodied AI. We've seen how advances like Prism and Gaia are helping us to simulate complex dynamic scenes end to end. We've seen how language can help us with explainability and building trust and understanding of how these end-to-end systems work, and how embodied AI foundation models are going to be one of the key levers to extend this further. So with that, I will wrap up. Thank you again for coming. You'll see us around. There's a lot of us from Wave here this week. We've got a booth on the floor. We've got the rest of the tutorial this afternoon, of course. And please come talk to me, talk to one of the team. I would love to engage and continue this conversation. Thank you.
Thank you, Jimmy. Thank you, Jimmy. So we have a few minutes for questions. So, yeah, you want to.
So you did explain about Gaia and how you can create scenarios, right? How do you go from, say, creating new scenarios where you can plug in stuff to creating the actual tail scenarios that we care about? For example, something falling off the back of a truck or something. Is that coming from user prompts that we write today, or is that also automated, or how do we think about?
Yeah, so I think so. The question is, how do you go beyond just sort of inserting vehicles to generating more complex scenarios? And I think that's one of the big challenges in simulation, right? Is it's not just doing it. I mean, I think that could be done by hand relatively straightforwardly, but the question is, how do you do it scalably? How do you do that? I'm not going to claim that I have all the answers to that today, but I do think that's really the crux of this challenge is how do you keep pushing the envelope there in a sustainable, scalable way?
You can generate rich and realistic data recommendations. Why don't we use that data instead of using foundation models? Right.
Yeah, so the question is, we can generate synthetic data. Why do we use those rather than foundation models? I'm not sure the answer is that you don't, it's one or the other. I think you can certainly think about both. And I think when you think about, I think it's especially around safety critical scenarios, they're not going to be things that you're going to be able to capture much of yourself. Now, there may be dash cam footage and in quite some volume on the web that does capture those kind of safety critical scenarios. But even then, I think there are very good reasons why you might want to simulate those more programmatically. I think you also very quickly get into the sort of interesting, almost philosophical debate about, is it better for a model to learn from the entire web versus, rather, what happens when the web is entirely simulated, it's synthetic itself, right? When ChatGPT is spat out almost every website on there, can you still learn from that? Can you still get value from that? I think there are some arguments both directions, but yeah.
Actually, great talk. I had a question about, do you think like Gaia and Prism are kind of becoming a virtuous cycle in that way, that first you get a real world scenario and then you use Prism to simulate millions of those scenarios and then go back to Gaia? So it feels to me that they're like kind of becoming one thing.
Yeah, I think there's definitely some convergence between Gaia and Prism. I think exactly where that takes us, we will see. But yeah, you can certainly imagine taking a fully generated Gaia scene and then resimulating that and that giving you more levels of control. I said, yeah.
Someone found it back.
So
You really showed some great capabilities from Lingo Gaia. I'm interested where in your like production pipeline of development, testing, validation, deployment, vehicle testing, evaluation, where do those tools play a prominent, if and where do they play a prominent role in data?
Okay. The question is basically where do all of these things that I talked about today show up in our production stack? I'm not going to talk about our production stack, so I'll say that up front. But the mission of the reason we have a science team at Wave, that we can invest in these kind of fundamental research breakthroughs, is precisely because we want to take that into production, and we want that to impact our stack, and we want that to accelerate the progress that the company is making. So I won't answer with any specifics for obvious reasons, but absolutely we are pushing these as fast as we can into production.
Is there any systematic way to evaluate the generated work that it resembles correctly?
Yeah. Can you evaluate the realism of the generated world? I think that's a really interesting question. And I don't know, maybe Jennifer will talk about it a little bit later on, but I think there's a more general version of that is how do you evaluate the realism of a simulator? And I think that there are lots of approaches, all of them imperfect, the ones I've come across so far. But all add a little bit of value. So you can look at, the realism of the generated scenes. You can look at how faithfully it's able to recreate an existing scene. If it's a fully generated one, though, it becomes a bit more challenging. But then, you could start to look at distributions of behavior in that simulator, things like that.
Question from a safety perspective. How would you anticipate or wish to see safety research change to be able to support this kind of end? What would you say to the naysayers effectively and convince their perception of what it takes to get this production?
Yeah, I think so. What would I say to the naysayers? Well, I think part of it would come back to that thought experiment I did earlier, which is would you put on an HMD and drive your car around the real world only seeing bounding boxes? I think that's part of it. I think part of it is that you can get the feeling of security from testing each individual box in that complex thing, but when it comes to the whole, you still have to test the whole as a system, and that's no different to what we have here. I think. And then I think the other thing is just the mounting evidence that actually it does work better in practice. And so because of that, I think you just have to, that doesn't mean we've solved all the problems around safety by any means, but we need to go and invest in that. And we need the community here to engage in that process and to be part of that and to, put that sort of skepticism of end to end aside and think, okay, this is happening, it's real, it's working. How do we now go and build that safety assurance that we need?
Last question. They're asking from outside. It's not broadcasted, so but we will have recording released later. We'll have recording released later.
But it's not like the room is going.
That's for the present one. Right. So let's thank again, Jimmy.
Thank you.
Let me welcome our second speaker, Hongyang Li. Hongyang is an assistant professor at the University of Hong Kong and a research scientist at Local Drive Lab, Shanghai AI Lab. His research focus is on autonomous driving and embedded AI. He's well known for leading the end-to-end autonomous driving project, UniAD, that won the CVPR Best Paper Award in 2023, and the bird's eye view perception work by Former that won the top 100 AI papers in 2022. Let's welcome Hongyang.
Thank you for inviting me. Okay, hello everyone. My name is Hongyang from Shanghai. I just arrived in the States, so there's might be some jet lag. And so my title, the title of my talk is could foundation models really resolve end-to-end auto driving? So how many guys of you vote for this? So foundation model will definitely resolve end-to-end autonomy. Okay. Really resolve or partial can resolve for the time being now. Okay, I see a few hands up, only a few. Okay, and how many of you have already come from the industry? Many hands, and the rest are from the academia. Okay, okay, only a few from the academia. Okay, that would be great. Because I'll briefly talk about the roadmap in the research because we are told I'm asked to give you a deep dive or walkthrough of all the recent end-to-end autonomous driving research, especially in the academia. So my talk consists of 3 parts. So the first one is introduction to the end-to-end and the data sets, the evaluation, and also the motivation. And the second part is some recent work from the community, not only from our group. And the last part is a few challenges and closing remarks as to what's the so-called future of end-to-end autonomous driving. Because I just came back from a few test trials, especially a Chinese corporation called Huawei, and another is from Tesla, and I also test a few other products. I mean, we just sit there and to test from like the from the source destination and to the destination. So I think most of the cases in the autonomous driving nowadays are well resolved. So the only reason that we are here is that whether we can mitigate the marginal gap between the resolved part with that of the corner cases part. So the first one is introduction. This is a problem setup. As we all know, autonomous driving consists of 3 parts, where the perception is about recognize the objects, whatever in whichever form, 2D bounding box or 3D bounding box. And the prediction part is given the ego vehicle. So how could you predict the intent or trajectory in the environment of the other agents? And the third part is planning, where you have given all the preceding information, whatever is perception results or prediction results, and you're gonna plan your own trajectory in the next few frames. So we do have lots of challenges. So the first thing first, as Jimmy already mentioned, I suppose, the definition of end-to-end in our case, in today's talk, is that this is a suite of fully differentiable programs that takes raw sensor input as input, raw data, I mean, whatever camera, LiDAR, canvas data into the system, and then produce a plan or low-level control actions as output, which is shown in the red block here. So compared to the conventional module-based design, where each module or functionality would output the direct results in whichever form you can name it, mapping results or bounding box. So in the end-to-end paradigm, so each module would feed forward the features or representations, and you only got you only got major objective functions or training loss to get back propagated through the standard deep learning optimization process. So this is the major distinction from the end-to-end compared to the module-based design. So there are also some preliminaries. The first one is data sets and evaluation. So as I mentioned earlier, we are tasked to do the planning task, which is to perform a few waypoints or trajectories of your own ego vehicle in the next few frames. So there are some renowned data sets. The first one is nuisance. And I think all of you no nuisance, right? So the behavior or interaction, I mean, the behavior of the surrounding agents with the interaction with your own ego vehicle is realistic. It is captured from the realistic data sets. And the strategy here means once the data set is collected, you cannot modify the trajectories, right? For example, from point A to point B, as long as the data set is collected, so the trajectory is fixed. So this is called the open loop evaluation. And for the metric, which means the metric is to evaluate how well you did the trajectory prediction or other tasks, is the L2 error. And I think the other, the rest data sets like Waymo or Argos is also very famous, and it is performed in the similar way. And recently, we see the new plan dataset benchmark. It consists of way larger, at least a 1 magnitude of scale of the length of driving scenarios compared to the previous new things Waymo and Argos. And it is machine learning based, collected, and it is closed loop. So by closed loop, here we see, so the nexus surrounding environment is dependent on the current prediction output of your own algorithm. So in terms of evaluation, it got a various metric, whatever you can evaluate in the average displacement error or in the collision rate or the a comprehensive score called PDN score. So basically, it is a weighted sum of 5 or 6 evaluation metrics. So for the details, you can resort to this awesome GitHub repo. And the rest part is a synthetic generated data set. So to name a few, I think the most famous tool is DriveSim. But unfortunately, I never saw a technical report or some open source repo from DriveSim. So over the years, it's a lot of demo, and I could admit it's very fantastic. But we are from the academia, we only see the technical report as the solid evidence. So that's why we are using the Kala, which is all open source, and it can be it can generate unlimited data because of a simulation, right? You can manipulate all the environment as assets, and it's handcrafted, and it's open. It is open looped and it's closed. It's open source and it's evaluated in a closed loop. So in the Kala, it has a driving score, which consists of 2 parts. The first one is how complete are your whole route finished in a given mapping town, multiplied by the infraction penalty, which if you collide with somebody else or with the environment, so you're going to be punished. So this is the data set. So why do we need a end-to-end? So over the years, I've been giving some talks as for the reasons. And as I prepared last night, I see the most straightforward motivation on this is the global optimization ability, which means this is example from a work called UniAD. And since each module is connected by the features, not the direct results. So even though here the red circle, so this is the perception results where you turn, in this case, you will turn right. But the car doesn't see there is a obstacle behind the tree. So even if the perception fails, and we can see during the feature attention feature layers in the planning part, it can also regress all the attention part. So my takeaway is that in this end-to-end paradigm or paradigm shift, you can recover from the previous module's failure, even if the perception is inferior and you didn't recognize the objects. But compared to the conventional part, which is a modular design, you cannot even ever do that, right? So I think this is the most important motivation for us to do the end-to-end. And another thing is the emergence of foundation models, which is a scaling law. So we have a massive amount of data, and you got assuming you have a lot of GPUs or infrastructure, and you can show or demonstrate strong generalization capability. But to be honest, I haven't heard any or few solid evidence to claim that we are doing the foundation model for auto driving. So I think most of the audience came from the industry. I must assume you have a lot of GPUs or data. So please, if you have these resources, you can share some public results in a technical form. And so what we are seeing here, all the way here, is that I think we are here. I mean, the green dashed line here is the end-to-end approach, but it hasn't shown very promising results or capabilities. And as I mentioned earlier, if you ever test some trial drive in this daily, like Tesla FSD in their vehicle, I think most of the cases are well resolved. So why we are sitting here, or why we are doing research, especially in academia for autonomous driving. So all the way here, we are resolving this part or this gap. So to mitigate what the non-end-to-end system cannot do, and to exhibit great generalization given the faster development from the foundation models are essential. And this part is for the efficiency. So in my previous talk, I think efficiency is the good part, but I really think this is not, especially you are deploying the large foundation models. So the FPS of foundation models is below 10, but as I know from the industry, this requirement is at least for 30 or even higher. And the only downside part, I think, for the end-to-end auto driving is lack of interpretability, which I think this problem resumes in all computer vision domains. This is because due to the end-to-end neural network, you cannot explicitly explain which part takes the major responsibility. And someone may argue, okay, you have the unfair evaluation as to the open loop or other parts as for the simulation. But I think those are the challenges. Those are the challenges that can be solved, whatever from the academia or industry. So those are not the disadvantages that inherently resides in the end-to-end paradigm. So given the limited time, how much time I left? So this is a classic algorithm. It's called the transfuser. And you can see here, I will just skip that. How many times I left? Where's that? Okay, he's nowhere. Okay, so I'll dive into this part. So this is the UniAD paradigm, and I think, okay. Here, this is a little bit credit here. I must to say that given the limited time. So all the way back to the end-to-end system dates back to this project called OpenPilot. So I think this is a startup company in San Diego. I see their CTO are very active on Twitter. And we really bought their equipment and tested in Shanghai. And this back to 2 years ago. I think this is the first time that drives me to see autonomous driving can be such a simple thing to use a simple network to directly output the control signals. So if you have some effort or have more interest, I would strongly encourage you to buy some product from them and test it in your own car. Okay. This is a personal advertisement for this. Okay, and the second part is research panorama, which is I have skipped some conventional approaches, the introduction of them. So the very original end-to-end can be dated back even into before the 20s, where I think this comes from some blog from NVIDIA, or I'm not sure. So the input is even black image and relying only on the neural network, which is just 3 MLPs. and you can have a control system. And then here I omit a lot of related works here before the 2020. So here, so the y-axis is a goal. I prefer to use the word goal. You can refer to it as performance, or if you are from the industry, it indicates the MPI. If you are from the academia, it indicates some performance score on some specific benchmark. And recently, we see the UNAD and many others. For example, VAD, I really like VAD work. Is way efficient than the UNAD. So the gap or the gain from the previous work, I think, to my opinion, is a formulation which we should shift from the modular-based design to the end-to-end. And there is no scale of data. I mean, the size of the circle indicates the data scale because they are all doing on the new things, well-studied new things. And we all see from the industry, there is a hype that you can utilize different end-to-end auto-driving system. At least in China, I think literally every car company claims they have deployed the end-to-end system. I'm not sure whether this is the case in Europe or the States. So for example, I've seen the advertisement from Mobileye in CES this year, and also other Chinese corporations, just to name a few. And I think there are some concurrent work, which is Gaia and Prism, which is released yesterday, a few days ago, and also the JAD or Lingo other work. So to be honest, I think the marginal gap is the gain is really marginal because I think the data scale helps, but VLMs or LLMs should do better. I could talk about this topic for the whole day, but given the time, I should first put the conclusion here. So given on the future, so what's the future? Should we fully leverage all the data given from the large amount test scenarios from the simulation or the so-called embodied AGI? So what should we do? So my takeaway or missing ingredients consists of 4 parts. The first one is the data. Everyone knows about the data, right? And the second part is this is where the university faculty or research students steps in. So we can still do a lot of technical contributions in architecture, whatever you are using the dual system, or you are using the word model, or using the video prediction, such as what they do in the Sora. And the last missing pieces is the info of platform. I'm not sure if any of you or most of you have dealt with training with hundreds of GPUs. If you are doing this, you must much remember that the training stability is very important. And also the deployment. How could you deploy the large-scale foundation models on board? I've been asked 1,000 times, even though I came from the academia. So I think that's a major responsibility from the industry. So let's take our respective role, okay? So my take on the generalization to achieve the end-to-end autonomous driving system starts with the data. So we have the we have to collect the massive amount of data, and then we have to think about the effective action or policy learning. How could you utilize the whatever reinforcement learning or imitation learning? Here are some examples of previous work from our group or from the other groups, including the MP3 or UNAD or driver adapter. They are mainly focused on the algorithm part. And also, as the emergence of LLMs, we got interpretable causal reasoning, whatever you are utilizing the LLMs to interpret the scenarios. But for now, for the time being, as of today, I see no evident improvement given from the large language models. So one of the reasons is probably that the output of the conventional task in auto driving, whatever is planning or motion prediction, requires numeric or exact trajectory outputs, which is for the LMs is incapable at all to output the exact numeric numbers. So we will see a lot of LMs in the driving scenarios, right? And most 99 of them got rejected by the CPR or by other conferences. So I think the major takeaway is that yeah, the LM doesn't express the very good results or generalization as shown in the other domains, such as the general vision domain, as it is shown. So then we got the closed loop simulation. Closed loop simulation is really important because you have to interact with the environment, right? So the trajectory is not fixed. As long as the algorithm has some output, the environment has to shift according to your algorithm. So in such case, the end-to-end auto driving can be deployed with zero gap to the production. Otherwise, it's only a prototype stage. And then we got, once you have the closed loop simulation, you have the demo collection where you can collect a lot of safety critical scenarios, and you can design reward or other feedback depending on your algorithm design, whichever is imitation learning or RL. And then it comes to the safety deployment. Okay, so I'll just walk through a few works. If you are taking it seriously, there is a very good survey paper written by Lichen. I'm not sure if he's here or not. So we have summarized all the detailed work and grouped them into together. And we draw the color driving score here. And so if you are seriously want to work on the end-to-end auto driving, I would highly recommend it. So I will also skip this part. I will be a little bit lengthy here. So we have a poster on Thursday. I'm not sure. So this part is as I said earlier, right? We are in the age of foundation models. So how could you utilize all the YouTube data, or how could you express good generalization ability? So this is the motivation of the GenAD work, where we utilize all the internet data from the YouTube driving cases. So as you guys can see here, those are all the driver videos in the front view. So it has seen almost all the globe in all the continents. So using this paradigm, you can for sure using the self-supervised learning or unsupervised learning to see the potential of creating a foundation model in auto driving yourself and see how it performs in the downstream tasks such as planning. And the other work is, I will skip that. We really got a lot of the slides. And the next part is the Vista project. So I really like this project. Is recently released on Archive. And so given the Vista work, the GenAD work, we have limited data on new things, or we have the representation capability, which has a very small scale of resolution in auto driving. And also the control flexibility, which means previous work using only a single modality or compatible with planning algorithms. So in this work, we have built on the GenAD dataset, which consists of more than nearly 2,000 hours of driving data. And then we have the resolution is much higher compared to previous GenAD DriveGAN or other works. And also we have more control flexibility. But yet again, I think this is a very marginal work because we are still facing the problem. Okay, you have the foundation model for driving, then what? So how can you apply the foundation model, how can you drive like a human driver? Like we are using these foundation models, not to mention the deployment thing. How can you drive smoothly and in some out of nowhere cases or in some corner cases, you can generalize or right? This is a core capability of foundation models. But for the time being here, I haven't seen any work that has claimed such capability. So most of the work just stop here, which generates the very fancy Sora version in the driving cases. So this is where our university students or research scholars could invest lots of time to work on. So this slide shows a few bits of Vista, which exhibits high fidelity in the future prediction or continuous long horizon robot. I knew this is nothing new given the emergence of Sora, but in the driving, at least in the driving domain, I've never seen such high resolution or long horizon. I think it's 50 seconds or 20 seconds, I'm not sure. But again, given the amazing performance of Sora, someone say this is no big deal, but please show your work, okay? And this is a zero shot action controllability. I'll skip this part. It's just more better performance. Okay, so this is the last part. I'm sorry for the lengthy talk. And this part, I really want to see the challenges or closing remarks of what's the future or what's next in the auto driving. Because nowadays I'm often asked, does it make sense to do research in the university? So my guess is, so if you are doing the perception or prediction on conventional benchmarks, no offense, is probably that. I mean, what's the big deal of improving 2% of mean AP on new things? Let the task be resolved by the computer vision domains. I mean, there is a whole bunch of people doing object detection in this whole CVPR, right? The reason of all of you come here to this room is to resolve real world problems for auto driving. We are a applied science domain, right? So I really think there's no big deal to work on this. So please stop doing some research on new things. But no offense, Holger, we are very close friends. He just visited us in Shanghai, but no offense to new things at all. I mean, this is a great work. Okay. And previous hype indicates last year we got the end-to-end trending topics. Everyone talks about it. And nowadays we have the new baby called word model, dual system, and other neural rendering techniques, right? So for the academia, I don't have too much results. Is there any impact research left? So my opinion is maybe in occupancy or in mapping or in motion prediction, I don't know. Maybe there is. But for the industry, we often heard we have lots of GPUs, millions of driving data, but we cannot get access to it. So could we beat Tesla or other winning corporations, no offense to other corporations, and achieve L4 once for all using end-to-end? So my answer is definitely not. And because there are just so many unresolved challenges. So if there is only one page of takeaway in this talk today, it's going to be next one, this one. So I have at least several dimensions in terms of data. So we need high quality or large scale data. So this is just a rough division of research and engineering. I'm not leading to either part, okay? So for the academia, I think we need some research, especially using neural rendering, whatever Gaussian splatting. We can see lots of amazing work from recent CVPR or CGraph to generate high fidelity or controllable simulation as the word engine to interact with the environment. So we see some counterparts in previous year. So the very exemplar is color, but it doesn't do well, right? Everyone knows that. But I haven't seen any well-popular platform or open source project than color. So I think doing this part is really impactful. And also for the engineering part, everyone knows that is a scalability collection. So recently I heard this book and I have checked some chapters in this book. It's called Human in the Loop, Machine Learning. I would strongly recommend you guys to have a look. So for now, I would say we would, in order to achieve the foundation model, we need at least 10,000 of hours. Given your reference, new things is only 5 hours. And 80% of them are just going straight scenarios, okay? So do not report any me AP on new things to me or to some conference again. We just need to have too many archival papers each month, right? And for this CPR is, okay, let's skip for that. And we can see that I just take this photo from the Twitter. This is a reference on the FSD. So this is the unit per billion of miles. So after the emergence of V12, which utilized the end-to-end, according to them, right? So their data just blooms like exponentially. So we really need a lot of data to achieve this. But this is not the responsibility for one single corporation, but instead it does need a reunion from across countries or across many efforts from different parties, right? So the second part is the algorithm or methodology part. I could also elaborate or explain in many hours. So for like, given the word model or video generation, we can do, so these are the techniques or the tools. This is why I put in a smaller fonts. So nowadays, many people just say word model is the only solution to all of that stuff. But in my opinion, it's just a tool. And the red part is the goal or the task. We need to achieve the closed loop feedback or to achieve the long horizon planning. And also for the engineering part is the efficient, which is the deployment, which is a 4-hour topic that we are going to discuss. And to achieve this, the tool should be the dual system as to system 1, system 2, or model compression or whatever novelty is going to be there in the perception module. And also some people might see in the future, is it solely based on the end-to-end or solely based on the module-based design? I would say it's not a dichotomy. It's not a yes or no. I would say it's an explicit design with explicit design, whichever something like in the UniAD where you have the perception, but it's still in an end-to-end system. Okay, so for this, I would strongly recommend you could resort to this embodied AI survey paper. I rarely recommend papers nowadays, but this is a really good paper that you can reference to. I draw many insights from this paper. I think this is from the Google DeepMind team, but it's another team. Okay, and the last part is the compute and infra. Surprisingly, I see just a few discussions in this conference to discuss about it, especially we are doing the autonomous driving research. If you're doing the foundation model, I think there are just, you need many GPUs, okay, for the university or not. And this is not indicating the whole group. I mean, for one project. So if you are doing the GenAD or Prisma, I'm not sure Prisma use, I'm even not sure this is secret or not. But for me, I think if you are seriously doing the foundation model for autonomous driving, at least 50 or so GPUs per project is needed. And if you are staying in the industry, I think at least 1,000. Yes, I think so. And the stability or how to guarantee faster I/O or other hardware issues are also very critical. Okay, so we have switched the research paradigm. So a few years ago, people might think you might only focus on the novelty or algorithm technical contribution. But as the large foundation models, I think all the people in this room would agree that data and also the infrastructure also matters way better than the technical part. So again, this is a very brief challenges. And for more details, I would strongly recommend the survey paper that we wrote a few months ago. So it has more details on that. And finally, the task or the goal should be the same, whichever you are from the academia or the industry. That is to achieve the driving comfort or experience considered, at least consider in your research. Okay, so this is my opinion on that. So the final of the final is to how to achieve this AGI goal, this climbing to the Mars, utilizing lots of tools, whatever you are using, LLMs or with models or whatever. So data as word engine, as I mentioned earlier, and algorithm, you can do a whole bunch of things here, whatever is on each topic. And info and platform and deployment. I think those are all very important ingredients to achieve the end-to-end auto driving. So with all that, thanks for my team. And a lot of guys have just arrived in this CPR. And they are all the author of the retrospective work. And you can say hi to them. Okay, that's all for my talk. Thank you.
Think we have time for maybe one or two questions. I see the first hand was there at the back. Great timing.
I'm from like software ability software analysis domain, and we push to end-to-end big models that are interesting. Because in engineering, there is also the complexity of the real world that involves implementation. And one big reason for this is like if you observe a bug in the system, you can trace in the fault component,
yes,
the bug, fix it.
Yes.
These huge end-to-end models which are essentially.
Yes.
Repeat the question.
So the question is, how can you interpret or track all the bugs given some system in an end-to-end sense? So unfortunately, this is the very true downside part or the disadvantage part of the end-to-end auto driving, because if you are using a model-based design, you can easily track which part, the recognition or the prediction, whatever. So this is where, there is a workaround for now, is to have a explicit design where you have intermediate losses or intermediate outputs. And when the planning or the vehicle suddenly collides with the road, and you can see the intermediate results of the perception results from the network to see whether or not it fails or not. But it's still an intermediate solution for tracking the bugs. Okay.
One more question and then.
Yes. Yeah, thanks for the nice presentation. If we look at the future of the end-to-end solution, and let's say it is a system of networks of differentiable methods. And if we then zoom in on the first part, the perception part.
Yeah.
Do you think in the future computer vision tasks such as a video panoptic segmentation or other dense prediction tasks, will they still be relevant as a method to initialize that perception module or as a form of deep supervision, or in the future, we don't need these computer vision tasks anymore?
I would not go that extreme,
okay.
But my bet on this is yes, do not do segmentation or tracking on the driving again, because OpenAI or other expertise from their part can do it very well, and then you can utilize the VLMs to fine-tune on the auto driving. I mean, the segmentation, whatever the task, right?
So all that research at CVPR is not that relevant, at least not for autonomous driving.
Yeah, especially given the large scale of data and you can verify the scaling law, etc. thing, right? Right, that's my personal view, right? Do not propagate that.
Oh, it sounds sounds sensible.
Okay, sure.
All right, thank you very much. Let's thank our speaker as well. And we have a 20-minute break. We'll be back at 3:15. So please come back for the next talks.
So yeah, thanks for joining today. My name is Nikhil. I'm a lead applied scientist at Wave, focusing mainly on offline evaluation using tools like GhostGym to sort of validate our driving system. And today I'm going to talk about how we use neural simulators at Wave and also how we're looking at measuring progress in this field. Cool. So just a quick overview of the agenda today. I'm going to talk briefly about how we are using neural simulators at Wave and why they're needed in the AV 2.0 field. And then I want to talk a little bit about how we're thinking about benchmarking environment creation for neural simulators, as well as talk a little bit about the new data set that we're releasing to help inspire progress in the field, and then some concluding remarks. Cool. So why do we need a closed loop simulator for it, right? So I'm sure if you guys have been to Wave presentations before, you've seen this slide many a times. But this slide highlights the differences between the classical AV 1.0 approach and AV 2.0. So if we look at the AV 1.0 approach, it's sort of a very modular stack that where we go from have a pipelined approach of sensors in perception, planning, and control. As opposed to this, if we look at AV 2.0, we have our sensor input coming in, and we have one neural network that is optimized to do both perception and planning in parallel. So this is a new way of thinking about driving, and instead of trying to solve it with robotics, we try to develop a system that mirrors the way a human thinks about driving. So given this, what are the implications for how we actually design our simulators to accommodate this? So if we look at AV 1.0, and if we look at sort of validating the two big components in the stack, being perception and planning, we can start with perception on the left. So in a perception system, there's no sort of decision-making component in the system. So we can actually utilize open loop data to validate the accuracy of our perception systems. Since there's no decision-making component, there's no domain gap between offline and online predictions. And so this is a very effective way to benchmark perception systems. And on the right, if we look at the sort of how we validate planning systems in AV 1.0, since the planning stack operates on top of the outputs of the perception system, we can actually do this closed loop. We can do this closed loop simulation directly in the perception space. So what this means is the closed loop simulation engine can actually be it's a much simpler task, given you don't have to actually synthesize novel views directly in sensor space. Whereas if we look at AV 2.0, and given we're doing perception and planning in parallel, we need to actually, to develop a closed loop simulator, we actually have to synthesize novel views directly in sensor space. And on top of this, not only do we have to sort of render things directly in sensor space, but they actually have to be very photorealistic, and the domain gap to the real world has to be low. Yeah. So if we then look at how we actually would use or how we think about development of AV 2.0, one of the big desirable properties is when we observe a disengagement in the real world, we don't want to make the same mistake twice. So here's an example where we have a real world disengagement, where we have the model, where we have an empty zebra crossing in central London. And we can see that the driving model and control sort of unnecessarily slowed down at this empty crossing, which is not desirable, given you can sort of continue at your current speed. So given this disengagement, now we really want to make sure that we never have the same disengagement again. And we want to be able to sort of prove this with our offline systems. So if we start to think about, how we can actually go about doing this, what are the options we actually have here? So the first option is open loop verification. Here, we're just using the logged sensor data from the real world and running it through the next iteration of our driving model to measure how it would perform in these log states. So the really good thing about open loop verification is the domain gap is 0, given you're actually using the real images to run through your new model. So it's very, the predictions are actually very indicative of what would be the prediction at these states in the real world. One of the difficult things with open loop verification is because it's open loop, you can't actually see the outcomes of the decisions that the model made. So what this means is you only really get directional signal about how the model is improving offline. So if we look, for example, at this video on the left, we have a new model being tested in these log states, and the waypoints are in orange, whereas the original model is in blue. And we can see that the new model is predicting a much more consistent speed going through the zebra crossing. But still, given this, how can we actually know if this sort of prediction was sufficient to avoid a disengagement in the scenario? It's very difficult to do, even as humans, because we don't actually know what the next prediction at the new state would have been. But with that being said, open loop verification is very cheap to run, and we can scale this to thousands, if not millions of scenarios. And at this scale, the directional improvement can start to really provide valuable insights. When you have millions of these tests running and you're getting directional signal on each one of these tests, you can actually start to make, you can actually start to provide scores for the new model and control. So after open loop verification, another option we have is sort of creating a hand designed digital twin, similar to the engine like Carla. The main advantage of a system like this over open loop is that it's closed loop. So you can actually see the outcomes of the decisions that the model made. But even with expert technical artists, generally the domain gap remains quite high to the real world. So it's very difficult to make the jump and say, if we have a hand-designed digital twin of the scenario, it's very difficult to make the leap and say that this disengagement wouldn't have occurred in the real world as well. And once we actually move to the resimulation domain, this burden on technical artists actually increases even more, because they not only have to sort of create realistic looking assets, but they actually have to match the distribution or the assets we saw in a particular scenario. And so scaling these kinds of systems to every disengagement you see and want to create unit tests with is really difficult, since the main bottleneck here is the human effort to create the environments. And yeah, now if you look at the third option is using a neural simulator, which we all love. So if we look at the properties of a neural simulator, it's also closed loop. So you can actually allow the model to change the state transition away from the logged images. So you can actually start to move away from just observing decisions and move towards looking at what outcomes would have been. A neural simulator is uses a data-driven environment creation, which because of how the optimization of the environment is done, it is directly trying to match the real world distribution of the scenario we see. So what this means is there's no requirement for a technical artist or a human in the loop. We can pass video data in and get 3D or 4D simulation out. And this makes it super suitable for the resimulation use case, where we actually want to take the scenario we saw on the road, replay it offline, and allow the new model to actually control the actually have control of the state transition. So now if we look back at the original example we started off with, so again, we see on the left that we have this real world disengagement of the model slowing down. And on the right, we can see the same model we saw before with the orange waypoints. We now see it being tested in Ghostim, where we can see the speed stays consistent through the zebra crossing and doesn't have this dipping behavior. So we can actually now see that the outcome of these predictions compounded, and we can make more, we can with more confidence make statements and say that the new model wouldn't have also had this disengagement. And for us, this is huge because being able to do this offline, I mean, when you go in the real world, you'll never see the same situation twice. And so you need simulation to actually make comparisons between two models on the same scenario. And we're seeing a shift in this direction throughout the industry, not just at Wave, where Unisim from Wabi, NeurAD, just a few examples, but we're starting to see the whole industry move in this direction of utilizing data-driven techniques for simulation. Yeah, and now, I mean, one of the big aspects of a neural simulator is the environment that's used to actually represent the world in the simulation. Earlier this week, we announced Prism 1, one of our works to reconstruct 4D scenes directly from video data. And it's used in Ghostim, our neural simulator, to actually synthesize the environment such that a new driving model can be driven offline. So today I want to look a little bit deeper into the environment generation and how we can start to measure our progress towards creating better environments. So yeah, how do we actually measure the quality of these reconstructions? So first and foremost, we gotta keep things simple. We gotta have image-based metrics. So these are things like photometric reconstruction quality metrics. Pick your favorite metric, PSNR, LPIPS, SSIM. They're all super useful in being able to actually benchmark and test the quality of how our environment, how our simulated environment matches the real distribution. In addition to this, we can use geometric cues such as depth, surface normals, etc., to actually make sure the environment is not only photometrically accurate, but also geometrically represents geometrically represents the true scene that we see. Next, we have downstream metrics, right? So one of the use cases we have is resimulation. And so to go beyond just image-based metrics, we actually want to measure how low the domain gap is in the use case that it's going to be used for. So one of the big metrics we use to actually benchmark our environment creation is what we like to call reproducibility. It's pretty intuitive in that what we are trying to measure here is we take the same driving model that drove in a scenario on the road, we run it offline, and we measure how different the observed trajectory is offline to online. And this gives us a measure of the perceived domain gap by the driving model between the real world and the simulation. While this does benchmark the environment creation itself, it also provides a metric on how well we're able to actually resimulate the robot, things like the latency, the latency, the vehicle dynamics model. So it's not isolating just the environment itself, but it's sort of a better measure of the full simulation system as a whole. But nonetheless, super valuable to actually measure how the fidelity of the simulation. And another metric is novel view synthesis. So this is sort of in some sense, a privileged metric in a lot of ways, because you want to somehow measure what the image quality is when you're away from the sort of training views you use to train the environment model. So especially in domains like driving, this starts to become very relevant because most of the captures have these linear types of motion. Out there, at least for autonomous driving, where we're able to effectively benchmark how well we're doing in these off-axis poses. And yeah, we need to have this such that we can make progress in the field. So yeah, I want to take this opportunity to then sort of go over, why we need this and what's out there today, and how we at Wave are trying to help make progress on this and solve this problem. So if you look at benchmarks in machine learning over time, we see a pretty clear trend here that once a benchmark is sort of established, we get closer to human level performance, eventually surpass human level performance. And then we find that, these data sets are no longer effective ways for us to actually continue to make progress in the field. So we can see this on the left. We started with image classification. We crossed human level performance. There was a need for harder tasks to measure how well we're doing. So we moved to reading, language, and then eventually we go to competition math. And once these benchmarks are established, the community is very good about optimizing for these metrics and eventually surpassing human level performance. So if we look at image classification, I mean, the classic example of how this started is ImageNet. And ImageNet really arguably started, or was the base data set on top of which the deep learning revolution started. We had lots of innovations here, like AlexNet, Dropout, ResNets, many, many more. And it was really crucial in the early days of computer vision for us to measure progress in the field. But eventually, we got very good at ImageNet, and there was a need for something better. So what do? We sort of moved to harder perception tasks. We moved from global image level classification to tasks like semantic segmentation, which required us to not only give a class for a full image, but a per pixel class ID for images. And we also moved to tasks such as visual question answering, where it required a higher level of reasoning, where, for example, in this pizza, you have to actually reason about what's in the image and the contents of it to be able to effectively answer these questions. So once we moved to these tasks, we were getting closer and closer to actual real world use cases. And these were very effective data sets and metrics for us to actually continue to measure progress. And I mean, now the computer vision benchmarks are much more aligned with how we actually are going to use them in the real world. So if we go back to sort of novel view synthesis and we look at how the same evolution happened here, I'm sure if you've trained a nerve or a Gaussian splat in your life, you've seen this tractor. It was a perfect first example of how we can measure and actually prove that this problem is solvable in a small toy domain. And while it was great initially for measuring progress, you'd argue that, I mean, no longer sort of the benchmark that people are using to benchmark new work. Then we move away from these synthetic data examples to real world captures, still very controlled, object-centric scenes, but moving in this direction of getting to harder and harder tasks such that we can continue to push the boundaries of what's possible. After that, we started to see even these examples. Most methods out there today in the NVS domain are pretty good at those problems. So we wanted to make the problem even harder and start making things move. So here we see some example of the early days of dynamic nerve data sets, where people sort of took these synthetic objects and started making some movements in them and try to see if we can actually get an algorithm that faithfully reconstructs these 4D scenes. And this is a work that I really like from the folks at Berkeley, where they talk a little bit about how we can actually quantify how causal and dynamic a data set is. So if you look at the data sets, or most of the data sets I showed you in the last slide, they fall in this right-hand side category, where we either have a very controlled setup where we have multiple cameras looking at the scene from different viewpoints, or we have teleporting cameras where we just have like random instantiations of various cameras in the scene. Yeah, but so these captures are actually, they don't reflect how data captures are going to happen in the real world. In the real world, you're going to have an iPhone, you're going to move through a room, or you're going to have a vehicle, a robot that's basically moving through an environment. And they're going to be capturing these videos in a causal manner through the scene, rather than having a teleporting camera or having multiple studio-like setups. So we continue to see, okay, now we've seen methods that are able to solve this problem in this controlled setup, but now we actually want to move towards this left-hand side, where we have models that actually work with data distributions we'll see in the real world. Oops. So one of the sort of big sources of causal data captures in the real world is autonomous driving data sets. So, I mean, great works, I mean, that we've seen, I mean, Kitty 360, New Scenes, Waymo Open data set. They're all great data sets for various purposes. And we see that the novel view synthesis community has sort of gone to these data sets to sort of further challenge themselves with data that reflects actual real captures and getting them to work in these environments. We look at these autonomous driving data sets, they're causal, they're dynamic, they're outdoor. So they sort of check all the boxes in terms of the difficulties of getting these methods to work in the real world. And so this is how the community is really starting to challenge themselves. But if we look at sort of how these data sets have been designed, they're mostly designed specifically for the use cases of perception and planning. So what this means is the sort of setup of the data set, a distribution of scenes that are present are all sort of optimized for these tasks of perception and planning, and are not necessarily choosing things that are hard in the novel view synthesis domain. We also see, I mean, from the previous slide, that these rig setups are all, they're 360-degree rig setups, but the amount of overlap between the cameras is quite minimal. In the image on the bottom, you can see the overlap between the cameras in the Waymo Open dataset. And this makes it impossible to actually have this metric of off-axis reconstruction quality, because you don't have any redundancy in views where you can drop out a particular camera view and use that for the purpose of off-axis metrics. And each of these data sets sort of have their own format and sort of storage and way to sort of access the data. And this makes a lot of sense given these are more general purpose data sets and have a lot of different challenges. But when you actually start to try to utilize these for NVS domains, it becomes quite tricky to integrate these data sets into existing frameworks. So because of this, we saw the need for a new data set that's particularly tailored for the challenge of novel view synthesis that we call Wave Scenes 101. So Wave Scenes 101 is an autonomous driving data set, specifically for this task of novel view synthesis. And I'll talk a little bit about the properties that make this data set unique. So firstly, the camera setup. So we really tried to curate this camera setup such that it would be the most useful setup for this task. So as you can see in this image, our rig consists of 5 cameras, 4 of them wide-angle fisheye cameras, the blue frustrums you can see in the image on the left. And in the middle of we have this, what we're trying to get to as an evaluation camera that you can use to actually benchmark how well your reconstructions stay off the sort of training axes. So if we actually look at what this looks like, if you look at the RGB views from a snippet of this data set, you can see that this image in red is the sort of front-forward camera that's we use for evaluation. And you can see on the 2 adjacent cameras on the left and right of the vehicle that can be used for training. So what this means is you have enough overlap with the training views that you can actually effectively use this as a metric for off-axis reconstructions, but also makes the problem tractable where you're not using like a camera that has no overlap and makes the task. It's at the right balance between difficulty and usability. So if we actually start to look at the sort of how the diversity of the data set and how we've tried to curate it such that it's suitable for this challenge of novel view synthesis, We collected data across two countries, so the US and UK, day and night. We've also tried to put a special emphasis on things that like changing illumination in the scene. So you'll see a lot of scenes that have things like changing traffic lights, brake lights coming on and off, blinking indicators. And this is really done to reflect the challenge of being able to faithfully reconstruct this in simulation. Dynamic objects, so you'll see vehicles, but also pedestrians, cyclists, and deformable objects that are generally very difficult to make work with scene graph type approaches where you sort of try to compositionally arrange the scene. Also things like exposure changes and variable distances traveled in each segment makes the data set a good sort of way for the community to measure what we're currently good at and what currently needs improvement. So just some visuals to give you a feel for what's actually in there. So here we can sort of see, we also want to benchmark static scenes. So here are some examples of static scenes you'll see in the data set across residential and highway, both posing their own unique challenges. One, you travel much further, and one, there's just a much more detail into vegetation and houses on the roads. Dynamic vehicles. So again, you can see two very different scenes here. One in central London with very sort of complex behaviors of the vehicles that we're interacting with at lower speeds. And on the bottom, you'll see, more of a American highway type scene where things are moving really fast, but maybe a less complex motion profile. In addition to this, changing camera exposure, examples like going through tunnels, lens glare. These are all challenges that we face in the real world, and so we wanted to sort of reflect these challenges and pick scenes that specifically highlight maybe more extreme cases of this in the data set. Deformable objects, or as we like to call humans. These are some examples of scenes where there's a lot of humans in the scene, cyclists, and really sort of can highlight maybe strengths and weaknesses of a particular approach. Changing illumination, talked about changing traffic lights. Here we can see two scenes with temporary traffic lights in the UK, sort of more classical American traffic lights in the below. And we've selected segments particularly where these state transitions happen. And so you can actually start to benchmark if you're able to model these state transitions effectively. This is another one. A tough one is night scenes and how we can handle those when we do normal view synthesis. You can see some examples of this. Lots of challenges here. Just lower light in general makes the problem harder, but also you start to see a lot more sources of active lighting in the scene, such as the ego vehicle headlights, but also things like other vehicles, lampposts in the scene. And so we think this can also be effective to benchmark works that are specifically targeted for things like low light or night settings. So that's a little bit about the diversity of the data set. We also want to talk a little bit about, just structure for motion format. We know in novel view synthesis, NeRF Gaussian splatting, call map is king. Sort of most of the academic community utilizes call map as a source of posed information as well as 3D point information. So we've deliberately chosen to provide all of our sort of posed and calibration and 3D environment information in this call map format, such that it can as easily be integrated into existing NVS code bases and projects with minimal effort. Here you can see an example, NeRF Studio, a very popular framework for training Gaussian splats and NeRFs. You can see sort of the ease and how easy it is to actually start training a model on a particular scene in the data set. This is all possible in about 2 lines of code where you just utilize some of their inbuilt functionality to actually convert the core map information into a format that they have, and then you start training. So this, we believe, will really reduce the barrier to be able to actually get more sort of people from the NBS community involved in actually benchmarking in autonomous domains and actually starting to test how robust their algorithms are. So, I mean, now if we look at this table again, so we've released 101 scenes to begin with. We are looking to add more scenes in the future, but we wanted to start with something small such that we can iterate and get feedback from the community on what's valuable within these scenes. We do now have a held out camera for evaluation, so we can start to actually get quantitative metrics on top of the qualitative evaluations we do for novel view synthesis. And it's specifically built for this novel view synthesis use case. And so it makes integration with existing libraries much easier. Cool. So just to wrap up, some final remarks, some key takeaways. So we've spoken a little bit about how launch simulators are key to accelerate the development of autonomous vehicles, and why they're sort of needed to actually do scalable closed loop evaluation for development. We've talked a little bit about how benchmarking of current novel view synthesis methods is primarily image-based metrics and application-based metrics, but are lacking novel view synthesis metrics, where most of the sort of evaluations are qualitative. And lastly, we introduced a new data set that we've released to tackle these challenges with benchmarking and novel view synthesis. And we hope to inspire more progress in the field with this, on top of sort of what we're doing at Wave to accelerate this field. Yeah, and this data set specifically curated for this task. And that's it for me today. Thank you very much. If this kind of work sounds interesting to you, we are hiring, so come get in touch with us at our booth. The team will be there tomorrow, and love to catch up with you guys.
I think we have time for one question. Go fastest hand in the room.
So if you could go back to one slide, which was on novel synthesis slide when you introduced that, there was a scene where you had a car approaching a traffic intersection.
Yeah.
Are you came from the right to green.
Is it this one?
No, I think it was one of the earlier slides you had.
Okay.
Yeah, well, like really at the beginning of the presentation. Yeah, on the right hand side. So one of the things that I noticed was there's a small artifact that appears right above one of the lights in the right hand image. And my question is, do you have pixel level control over the scenes that are reconstructed? And my motivation for that question is, how resilient are the metrics that you're using to ensure that there's no downstream accidental artifact that's generated during the reconstruction process?
I see. So if I understand the question correctly, so you're asking how much controllability we have over the over
the reconstruction to correct if there's artifacts, if there's ways to measure accidental artifacts that appear in that process. That way you don't include that in the training or the evaluation process later on.
Yeah, it's a good question. So just to repeat it for online folks, the question is how we can detect or detect artifacts that occur in the reconstruction, such that we can maybe exclude that data for use downstream use cases. I mean, one of the like we spoke about, generally measuring the quality, we sort of use a multi-pronged approach here, where we try to measure, I mean, if the artifacts in the sense of downstream reproducibility use cases. So that's one measure of how we can actually measure this domain gap. But I mean, the sort of challenge is really when you're getting off axis, right? So this is where we find that having held out cameras that are not along the views is much more reliable in actually exposing these bad geometric reconstructions or artifacts in the reconstructions. And that's really why we've tried to sort of go down this way of evaluating. Cool, thanks.
All right, let's thank Nikhil. And we're gonna have to move on, but there is another break later. If you have questions, just grab Nikhil. Thank you, Nikhil. Right. Okay, almost on time. Hello, everyone. I'm Gianluca, and I'll introduce myself today because those gone. But yeah, I'm Gianluca. I'm one of the scientists at Wave, and for the majority of the time I spent at Wave, I've been thinking about world models. And today, what I want to do is kind of go through the journey I've been to when I started learning about world models and to where we are today. So there's been quite a lot of talks from Jamie earlier today about how do we use world models, what kind of world models we build. So what I try to do here is, this is ultimately a tutorial, so I'll try to cover a little bit more about the literature about world models. So if you're interested in world model, you don't know what they are, that's probably a good starting point. If you're an expert about world model, maybe some of your work is in here, please give me a shout. And if I missed out on some work, still give me a shout. I'll buy you a beer, sorry about that. So quick agenda. Again, I'll start with a brief motivational, why I think world models are important, and then go through some of the what I would call standard techniques or techniques that have been widely applied to world modeling problems, and then dive deeper into like some specific work that I think is particularly interesting in world models for autonomous driving specifically. So again, as I said, disclaimer, the literature is huge. This is about 30-minute talk, so I couldn't cover it all, and probably I missed out on something. And if you have great pointers for me, I'll be very happy to learn more. So motivation, why do I think world models are a good idea? Again, I always start with this picture. You just look at this picture, can you tell what's happening? Like, do you have guesses? What's happening? What is the car on the left doing? Is it moving? Is it stopped? We don't know, but we have guesses, right? Then this is actually what happened is that car was stopped. We went around it, but there were multiple options there. And it was very clear to everyone in the room what these options were. And that's because everyone has an internal world model. We can access to that and we make decisions based on what we think is going to happen next. So, but where is this knowledge coming from? I think the interesting thing is like since the early humans start to like observe the environment, then they learn how to interact with the environment, and they basically learn these samples and they build this world model. And this is not just this world model is built on any interaction and observation of the world, and we use it to generalize to so many different situations. Like many of us probably haven't crashed the car into a wall, but we all know it's not great, right? And we avoid that when we drive. So similarly, machine learning models can learn similar concept in a similar way, which is through observation, interaction, and mostly observation interaction with their own environment, or even observing other agents interact with the same environment or a different environment, etc., etc. And this can be done by observing videos, interacting with the simulator, observing how other models interact with the real environment, and so on. So I think my motivation is like word models are part of the human intelligence and they should be part of any embodied intelligence. So I think that's why it's so important to go through word modeling and understand where is this coming from, how it started, how it's going, and hopefully some of you have the answer of how this is gonna go in the future. So let's start with a brief introduction of word modeling techniques. So I would say these word models, this is a paper 2018. I call it how it started. In brackets, I would say with neural nets. Word models started way before 2018, but I think this is one of the first papers I could find that approached word modeling using neural nets. And how does this work? So it starts with, if you look at the image on the top left, it's a autoencoder, right? So high dimensional observations of the word get compressed into a latent space and decoded back through reconstruction losses. Now we have a way of compressing high dimensional observation of the word into a very compact latent space through, in this case, was variational autoencoder. And what they did next here is to use the recurrent nets, because I would say in 2018, that was kind of standard way of modeling sequences and temporal, and especially like temporal sequences. And this paper started proving that you can learn both a word model and a policy through that schema at the bottom by interacting with the environment, and you can achieve state-of-the-art performance. So at the time that was done using the OpenAI gym environments, but they proved that forcing a model to reason about the environment and what happened next really helped learning a stronger policy. I think immediately after that, Dreamer V1 came out. That was 2019, and Dreamer V1 introduced this RSSM architecture, which is effectively a recurrent net with some fancy distributions being matched. I'm not going to dive too much into the details here. I put links to all the papers if you want to read about all the details. But I think what's really interesting in Dreamer, it was the idea that you can learn a word model and a reward model, which is observing the environment or even other agents interacting with the environment. And then you can train your own policy fully in imagination. So then when you start training your agent, there is no interaction with the environment. And they proved that by doing this, what you can do is learn a very strong policy. And again, at the time, they used continuous latency, so it was similar like a PAE type of encoder to represent these high-dimensional observations. And they proved using the DeepMind control suite that you can achieve very, very good results without even interacting with that environment, which is pretty important because when we think about embodying AI into a real robot that interacts in the real world, we can't just throw a robot out in the wild and allow it to make too many mistakes before it's a disaster, right? And so this was very inspirational at the time. Dreamer V1 was followed by Dreamer V2. I would say the main difference between the two models was they moved from continuous states to discrete states. And it was similar, so they learned behaviors fully in imagination from a word model that they could train from observations. And this time, this model achieved state-of-the-art performance on the Atari suite. So, right, so we see that we moved from one type of latency to another, and there is extended capability. And the Dreamer saga continues, and there is Dreamer V3, where in Dreamer V3, the authors start to propose a lot of tricks on how to train and stabilize the training of this recurrent net, which is not very easy to train. I don't know if you try to fit some Dreamer models, they're tricky. If you succeed at it, they do very well. And Dreamer V3, they show how by stabilizing the training and allowing to train and scale up these Dreamer models, they can start tackle much more difficult environments like Minecraft. So we started from very simple environment, the Mind Control Suite, went to Atari, in the end Minecraft. So we kind of see this improvement in type of tasks that the word models can help to solve. So I'll pause here because I've mentioned a couple of times discrete latents, continuous latents, et cetera, et cetera. So like if you don't know what these things are, it's just auto-encoding the images and videos. So there is some literature on how you can do that. So, and what's the goal here? The goal is to take a large representation or state of the world, like an image or a video, and compress it. Why we want to compress it? Because then the world model can treat this compressed representation, even in this compressed representation, much better than it can do in the high dimensional representation. So I just put some pointers here, but I'm expecting everyone should be fairly familiar with these things. So we talked about recurrent nets, and we're moving now to transformers. So Fenaki came out in 2022. I mean, similar to what happened in language modeling, where we're modeling sequences, everyone moved from recurrent nets to transformers, and we kind of started to see the same shift happening in the word modeling world. So yeah, Fenaki came out, and it's like one of the first papers that proved that you can cast a word modeling problem, which is video modeling in the end, as an X token prediction or as a mask token prediction. And here is like an example of what Fenaki could generate. These are like rather small images. They're quite basic. But also what they did is they started to introduce this concept that these word models can be prompted with text. So the idea is you have an encoder that allows you to discretize images and videos. Now you have a sequence of discrete tokens, and you can train your model to predict the next token or predict a mass sequence of this token. In this case, it was a mass sequence of your tokens. And when it's time to generate, you can just prompt your model to generate what you want. And I think this was kind of the first works that demonstrated that that's possible to do with transformers, video prompting. That's it. Slight digression, Iris. So this paper introduced, again, similar ideas from the past, which are from Dreamer. Again, prove that transformers can be sample efficient word models. So they show that have higher sample efficiency than the corresponding like recurrent net models. And in very similar setting of Dreamer, they managed to like learn a policy completely in imagination, which it's very safe when you think about real world deployments. And they proved that on the Atari suite, they could do very, very well. So I think for now, we kind of jump back and forth from models that want to generate videos, models that want to learn a simulator of the world to train a policy. So what I'm trying to hint is word models can be used for several things. And you'll see like going forward, that's kind of the case. But yeah, so don't be confused by the fact that some word models are used to learn policies in simulation, some are not. So they've been widely employed in the last few years, and I'm trying to cover the most interesting work that I found so far. And of course, I mean, hasn't been claimed as a word model, but this year we also saw Sora coming out as kind of impressive video generator. And with Sora, we started seeing the shift from transformer-based architecture, still transformer-based, but start to train these models using latent diffusion instead of next token prediction. And yeah, Sora, I mean, we all saw it, like realistic long video generation from text prompts. I would say this been done on unknown data sources, hasn't been disclosed, but it's probably large scale. And so we see this shift is when it went from recurrent networks to transformer to more diffusion-based techniques now. And last, I would like to mention, I know that the title of the talk is we're going to explore generative word models, but I would like also to mention that in the word modeling literature, there is an entire stream of non-generative methods. What does that mean? For example, this BJPA work from 2023 proposes a different idea where you cast a word modeling problem not as a I'm trying to predict what's next, which kind of takes away your ability to then generate samples, but you can still learn a representation that is word model-like in a non-generative way. So I'll just mention it because it exists. It's not really the main topic of my talk, but I thought it was important to mention it. So this was kind of a very brief overview of how the word modeling framework shifted in the past like 4 or 5 years. And what happened is world models started to be widespread in autonomous driving. So here I just put a couple of images from a couple of review papers that came out recently that discuss about how world models are being used in autonomous driving. And actually, yes, everything here, if you look at these images, everything seems to start about 2022. Well, there's not much being reported earlier, but I would say that before 2022, we were like already investing and thinking about world models. I would say very early on, about like 2018, we published the blog where we managed to train a policy and deploy it in a small car, Twizy, I don't know if you're familiar with it, learning the policy fully in imagination on a world model that would fit on real world data. And then we started investing more and more, where we started publishing papers about predicting the future, starting to train these world models, first starting from simple representation like predicting the future in semantic segmentation space, moving to like fiery that did it like in bird's eye view space. I know, and some of this work then started to get, and we tried to like kind of close the loop with what I've presented in the literature before, where in 2022, we published MILE. So MILE is a recurrent state model, very, very similar to Dreamer, that predicts bird's eye view segmentation and action. So this is effectively a model that has learned jointly a word model and a policy. We deployed this in Carla, and at the time, I think we got state-of-the-art results. Of course, things are gotten much, much better now. And similarly, at the same time, there was this work called SAM2, which is very, very similar to mine. I just wanted to mention it because I think the two works came out basically 1 week apart. We didn't know, they didn't know. We just found it, and we just found it. So that's another example where using these recurrent state models in Carla, like people were able to fit word models and a policy jointly. Right, so then we moved on from that, and the main reason is we tried to scale that up to real world applications, and we didn't really see the scaling curve that we wanted to do, so we decided to rethink what we were doing, and that's how we started working on Gaia. So Gaia is our way of rethinking scaling world models with data and compute. And so what's Gaia? Gaia is a world model based on an autoregressive transformer, and Gaia employs a lot of different modality encoders to compress images, actions, and text as a set of tokens. Once you do that, you can just take this multi-model sequence, align it temporally, and just model this as a sequence. So we did this last year. We presented it at, I think, SVPR last year, and I think it's in most of our talks. Today, we are now using it in conjunction with Prism, like for several things away. Yeah, what was impressive when we first saw is like we started seeing that these new world models that we were training started to have a lot of nice things that we wanted to see in world models. They started to show us that they are intelligent, they do understand the world, and this is one of the examples, right? They started to demonstrate us that they do understand multiple options. And so if you can take a word model, you can initialize it with sequence and start unrolling. And if you take a few samples, you'll see that there is quite a lot of diversity. And this example, I think it was in Jamie's talk as well, but again, it's one of my favorites because here is just the word model is demonstrating that they can understand that even the interactions with other agents can be different. There are like multiple options out there. And having all this information is really, really important when it comes to like make decisions for driving. And here, I mean, you can see that these video generations are not like pixel perfect, but the concepts and things that are really, really important that we should care about are there. And that was really remarkable when we first saw it. We were so excited. Again, I think this has been shown today again, but another mind-blowing moment for the team, it was when we first saw these results. We did force a ego vehicle to drift in the wrong lane, and Gaia can simulate other vehicles responding to our actions. Again, all of this is fully end-to-end, nothing is scripted, and it's just an emergent behavior that you get from training at scale. Again, we allowed Gaia to generate from text prompts, and here's some example where we just say, I want the weather to be sunny, rainy, foggy, snowy, and we can get very, very realistic samples out of it. Similarly, we can control for the time of day, and all the samples look realistic and respect the prompts. And I would say one other important thing here is like the long generation. This is just 2x speed. This is a 2x speed up in this video, but here we just started generating a video and stop. We kept going. This goes for like minutes in the future, and it was one of the first time that by looking into the word modeling literature, I could find something that is that stable for that long in terms of generation. So that was about like a year ago. So after that, we started seeing a lot more work coming out in word modeling for autonomous driving. This is just one of these examples, and we started seeing that there's been a little bit of a shift towards like latent diffusion. So Drive Dreamer is one of these examples. So Drive Dreamer is like a latent diffusion model that allows to generate videos from HD maps, 3D boxes, or actions. And it can also predict future actions. So once you can do that, you can look back your next action into your word model and enroll from there. And this has been trained on and evaluated on new scenes. And here are just some examples of what they can generate condition on like a 3D scene. And yeah, it's truly remarkable to see that so many different techniques can be just trained with data to understand the world. It's just kind of a proof that the intelligence and all the concepts from the world that you want to learn can be learned just from data. Here's another example where they show how once you put back the action that you predicted into the word model, you can drive within your own imagination. So what they show at the bottom is the velocity and the steering angle predicted by the model, and at the top is the video predicted by their own word. So they can basically learn to drive in imagination after that. Similarly here, like Drive Word model, another latent diffusion model. The main contribution here and difference is like we started, like all the videos I showed up to now, they're like single camera, right? When we think about deploying autonomous driving to the real world, all these deployments do have multiple cameras. 6, 7, 8, 9 multiple sensors, and they are very high dimension. So Drive Word model, I think, is one of the first models that came out that started demonstrating that this can be done with multiple cameras. The geometry across the whole cameras is fairly consistent with no prior geometry into the model. And also this model could also generate actions and was trained on new scenes. And the caveat here is you can see that these videos are a little bit jittery, and that's because once you start adding cameras, you can't simulate at a very high frequency. It's very expensive. And so this model runs at a frequency that is lower than all the models that I showed before, but they extended it to 6 cameras, which is really impressive. And again, if you look at these images and pay attention to like the consistency, it's quite remarkable. Right, and then a driver I came out. So interesting here, we started to see multimodal language models being added on top of word models. I think this is one of the first I've seen, and it was trained on new scene and some private data sets that have been disclosed, but the video generation here is conditioned on actions, and these actions are described by text. And there is a large language model involved into the generation. I thought it was quite a novel idea. We've never seen that before. But anyway, we started to see like diffusion and multimodal language models coming together in the word modeling world. And moving on from real world images, there's been quite a lot of work as well trying to do world modeling in a different space, which is this case for off-world is 3D occupancy. And here, an interesting thing is like what we started to see is like moving from like plane transformers similar to like VITs or standard transformer to like spatiotemporal transformers, right? Because when we think about the world and the world model, both space and time are important. While up until ST transformers, most of this work have model space and time as a unique thing, and that's more expensive. So Awkward started to do this using 3D occupancy maps, and I think after that, Wabi published Copilot 4D, and still this is the discrete diffusion model. The observation space is like LiDAR space. I think it was trained on new scenes, Kitty and Argover, so like more data sets, LiDAR point clouds, like a different like observation space. But again, all is the same ideas of trying to model the world and in a certain representation space and try to predict what happens next. And here's a like great examples from their blog where they enroll time and they show how they can predict LiDAR point clouds in different scenarios. And this prediction is quite accurate and like for a few seconds in the future, which is probably what you need for like planning. Finally, I think this was mentioned by someone else today, like very recent paper, I think it came out like a couple of weeks ago. And we started to see like more diffusion models coming into the world of world modeling and started to tackle high resolution video generation. So this model Vista is quite impressive video generation at a very high resolution. So this is the highest resolution I've found in the literature. And these are some example videos from their work, quite stable generation. And finally, also this one came out a week ago that I think the most interesting thing about this paper, they were starting, yes, they do propose a new generative model to generate videos. But the most interesting part here is they just don't limit themselves at showing that they have a new world model that can generate realistic samples. They try to close the loop. And closing the loop means they show results where if you analyze your failure patterns on your end-to-end policy, and you have a way of generating new data samples that tackle those failure cases, you can actually improve the performance of an end-to-end policy. The interesting result here was they demonstrate that you need both. You need a really good generative model and a really good strategy to identify and generate the samples that are which you are weak. And have a look at the paper, but yeah, the results are really clear. You can't just take a great world model, generative model, and generate random samples, throw them back into your training set. That's actually degrading your performance. And at the same time, you can't generate samples of things you fail at from a non-generative model that is not good. Once you have both, you start to see the improvement. So I am almost at time. So yeah, let me just wrap up what I tried to discuss today. Yeah, I tried to stay away from like just wave specific things. I wanted to like kind of try to cover a little bit what's out there because world models are starting to be out there, especially like in autonomous driving. We're starting to see more and more companies or research labs starting to investigate world models and invest a lot of them. So what do we have seen today here? I would say, yeah, we should probably, I hope everyone agrees that now world models play right now an important role in embodied AI and will play a massive role. So it is important to invest in them. And we've seen, I would say, 4 main techniques that are commonly applied in the world model, like something like Dreamer and recurrent models. We started to see like vector quantized representation that can take large spaces like images or videos and compress them into like token spaces. Started to see diffusion models, and we also briefly seen JPA models, which are these generative models to learn models of the world. And we've seen that all these techniques can get put into work for autonomous driving. And they can employ as data generators. They can employ to understand the world as a representation learning tasks. They can be coupled with behavioral learning. They can be used for occupancy prediction and further planning. So applications of world models in autonomous driving are widespread. And so, yeah, I would just like to leave everyone with just one question, which is, how do we improve them? How do we leverage them to unlock the full potential of embodied AI? And that's just an open question I'll leave to the room. Thank you very much, and I'm happy to take questions.
Thank you, Gianluca, for the great talk. Yeah.
You mentioned consistency, frame over frame, and also multi-cam. And then you also showed, I think maybe one of the guide videos that you said you let it go for minutes. Do you have an idea of how large scale consistent it is? Then second half of that, I forget if it's the Prism or Lingo scripted model, how aware of large scale would be to can tell you guys that like back to the same place and it's or any.
Okay, I'll repeat the question for online. It's mainly two questions here, and it's correct. So one is, if we have a sense when we generate from Gaia for like minutes, whether we look back to the same place. And the second question is, for other models like Lingo, does Lingo understand we went back to the same place and can tell us that? So to answer the first question is like, no, we've never seen really like looping back to the same, exactly the same place. And the reason is Gaia is effectively a transformer model. You just sample the next token. So in order to go back to exactly the same place, the way we model one single time step is like thousands of tokens. So unless you sample exactly the same thousands of tokens, we are not at the same place. The combinatorial space is exponential, and so usually we never seen Gaia going back to the same place. We have seen early on when we were experimenting with it, Gaia trying not to be very inventive and mostly like try to remember some places of the world that we have seen more than others. But we immediately started seeing that when we start scaling this up, that goes away. So he stops memorizing. And the reason is, or at least my understanding of this is, when you expose these models to significant amount of data, they can't memorize them anymore, right? So, and neural networks are extremely lazy objects. So the easiest way of solving that is not memorizing what you've seen, but is really synthesizing and like condensing the rules of the word that generated the data. And now they become amazing data generators. And so we stopped seeing this memorization and going back to the same place kind of behavior. Regarding Lingo, I have to be honest, I don't know. I don't know if we have an example of going back to the same place and Lingo saying we just go back to the same place. But in general, like all these models have fairly limited memory. So even going around the same, like one block and back, probably takes minutes. So it's very unlikely that these models, until they start fully generalizing to extremely long contexts, will be able to do so.
For example, by driving in reverse.
The question is, if we try to see how well I generalize while trying to drive in reverse. And yeah, the answer is yes, yes. We try to like drive in reverse, and because it hasn't been trained on a lot of data where we reverse, what it does, well, we have two samples. Interestingly, in one sample, we started reversing and Gaia did a U-turn, because that's how you start the U-turn. And in the other one, it stopped reversing and it started to go forward. But yeah, I think we never showed it publicly, but like we kind of stress test Gaia a lot more to the point that at the time of publishing the paper, what we did is we took one image of everyone that worked on this project's hometown, wrote in their hometown, and we started enrolling from there. So what we saw is it was mostly trained on UK data. So when we initialized it on right-hand driving, what Gaia usually did is went up to the left and kept driving. But yeah, he generalized it. It generalized quite well. Of course, the image generation was the same quality of the data we trained on, but like the concepts and even the behavior of I initialized this model on the wrong side of the road according to this model, and this model decided to go back to the right. I was kind of impressed. We didn't expect it, but started seeing all of these emergent behaviors.
During the sampling of the future in the Gaia model, we are shooting from multiple possible futures. This includes the behavior of other agents, like if one vehicle is cutting you or not, or yielding you. I was wondering if we have more deterministic control over the behavior of other agents during the sampling of our model.
So the question is, when we sample future from Gaia, and the future is multimodal, we do not control other agents' behavior. And so the question is there a way of controlling, having more control? Yeah, actually, yes, there is. I think I haven't included in this presentation because I tried to limit my tutorial presentation to paper that we published. But I think today Jamie gave a sneak peek of how we can do that with Gaia, which is, for example, the examples that we gave on Prism, like we can add agents there and control what they do in a video. And so, yes, we do have new versions of Gaia where we're working on full controllability of other agents through their 3D position, text, et cetera, et cetera. So it's something that we have in the works, but we're adding the ability to control better the behavior of other agents.
On the back.
What are your thoughts on training a controller based on the lane representation inside of the Gaia model?
Question is whether thoughts on training a controller or a driving policy, imagining the latent space. Yeah, that's definitely like interesting thought. I mean, a lot of these papers that we've seen have done that, so I don't think it's not plausible.
One last question.
You mentioned that the RSSM and MILE didn't scale data that work on Gaia. Can you mention what about RSSM didn't scale? Was it for computational efficiency of it, or what?
Right. The question is, I mentioned that when we tried to work on RSSMs, we didn't see scaling with data and compute. And what's the reason for that? So I believe that the main reason is like RSSM used to be trained with this idea of you have a prior distribution of what's going to happen next and a posterior distribution. So, and then you match those with a KL divergence. So when you looked at the whole optimization landscape, you had like your reconstruction loss, two moving distributions, and a KL loss, which if you don't tune correctly, collapses. So what we've seen is it wasn't as easy to just say, okay, let's double the parameters, let's double the data. You start training, everything seems fine, but if you end up in that weird space of your optimization where that those two distributions collapse on top of each other, the prior and the posterior, you're doomed. You forget everything. And we've seen that with scaling, we couldn't really control that easily. So it was really hard to tune all those hyperparameters. Whilst when we switched to Gaia, we reframed the whole problem as that's just next token prediction. And so there's only one loss, it's the cross entropy loss. And you're guaranteed that lower is better. Right. So in the RSSM formulation, you don't have that guarantee because what is better, like lower KL, better reconstruction, you have to trade one off for the other. So it made it very, very hard to scale just because you start an experiment, you start training well, and after a couple of days, it collapses on you. And then you're like, okay, let's start from scratch, change your hyperparameters and go back and forth. While with Gaia, what we saw is that double the parameters, scale a little bit the learning rate, go. And you see that loss keeps going. And if you don't stop, it keeps going, right? So I think that's what allowed us to really scale.
All right, let's thank again Gianluca for the amazing talk. And we're now having a coffee break for 15 minutes. Please come back at 4:50 there are two more talks on language for driving and also the future direction of autonomous driving. All right. Our next presenter is Oleg. Oleg is a principal applied scientist at Wave, leading the Lingo team. Oleg, it's all yours.
All right. They hear me well? All good?
Yes.
Okay. Yeah, so my name is Oleg, and I'm going to tell you about language in autonomous driving. So let's start with this kind of main question. Why would you use language in self-driving? That was actually completely non-obvious just a few years ago, right? So it all started at around 2018, actually, with a Berkeley Deep Drive X dataset. It's the first explainability dataset for self-driving. And in that first paper regarding explainability, this is a citation from that paper. They cite those main three reasons why would you need language in self-driving. First is user acceptance. Self-driving is a radical technology, so everyone needs to trust it. People need to understand and extrapolate the behavior, and also effective communication between the vehicle and the human. Then another thing is that before, let's say 2023, there was the main reasoning architectures before LLMs were mainly those kind of technologies. You guys are probably all familiar with Monte Carlo tree search. There are also a lot of planning in deep learning using graph neural networks and a mixing of semantic engines and deep neural networks. But in 2020, there was this discovery where just next language token prediction can make model reason. And this is GPT-3, not 3.5, where already in 2020, it can do very simple reasoning regarding self-driving, right? So you can see that I'm on the 3-lane road in the middle lane, I need to turn left. And what do you need to do next, right? And it auto-completes this plan. And this plan kind of makes sense. Yeah, there is a small mistake, but it's kind of okay for 2020. But think about it. It's completely non-obvious. Why would next token prediction make any model to reason and plan? Right. So when I seen this, I finally realized, all right, so then this is a technology, language model technology, is the one that would allow models to do planning and reasoning in one single architecture without any extra machinery like tree search or GNNs and so on. Another insight is that explanation is actually kind of equals to reasoning, right? So think about it. Imagine you see a person and then you press on the brake and then the model generate explanation. Okay, I'm pressing on the brake because there's a person on the street. Right? So if you just do this in codes kind of simple thing where you place this explanation before you do the action, suddenly the sentence becomes a reasoning sentence where you say, okay, I see the person and I'm pressing the brake because there is a person on the street, and then you press the brake. Right? So the single thing that happened is that you kind of swap the places here between explanation and action. And obviously explanation now don't have access to action. It's kind of a bit tricky. But you can see that explainable model actually is a reasoning model, which is kind of non-obvious fact that became obvious when LLMs kind of came on the scene. Okay, so yeah, another thing is language is a very nice compressed information medium. So take a look at this very complicated scene in central London. While it's all complicated, it's actually quite, it's not so long to just make a really nice description in text about all of that. My lane is straight only, the light is on my lane is green. I'm just attending to pedestrians, speeding it up. If you just compute those words, it will be like just 140 bytes, right? Which is it's kind of cheeky information compression, but that's pretty much everything you need to drive in the scene. And because it's such a nice information medium, there was this whole field emerged about that is called LLM agents that take language and use it in all sorts of different ways, right? And we in self-driving also can use all technologies from LLM agents to endow our models with those many advanced features that take advantage of this medium. You can have long-term memory, in-context learning, lifelong learning. You can interact with the user, obviously, and I'm going to show examples of all of that. And the last but not least is that edge case data for self-driving is particularly precious you know, to actually drive well, you need a lot of combinations of different objects and a lot of weird things going on. So people behaving weird, some animals on the road and so on. And before large pre-trained models, it was kind of non-obvious what to do. So you just, as a company or a lab, you have to collect all that data. But now, with the release of all that huge models that we can all use, hopefully they're still open source at the moment, right? There is like the second option for many robotic labs and companies. So before you have to collect this data yourself, but now you can rely on the large models that are pre-trained on that data, and you hope that you're just going to generalize to those driving cases. Okay, so then how would you add a language model into autonomous driving system? So for that tutorial, I reviewed many papers, and I'll share the slides later. So like there are a lot of links just to show that there are a lot of work actually going on in that field. And I mainly picked some papers which are about pre-trained language models and that appeared after 2023. But this is the prototypical system. How would you do that? So you take the input from kind of autonomous driving sensors. So it could be multicam vision or just scene state, LiDAR information. You pass it through this language bridge, which translates this information to tokens. Then you use a pre-trained language model, and you pass the output of that through another action bridge, and that makes a driving output that you can pass to the car. Additionally, you can have a language output, which obviously tells you explanation and reasoning. And then on top of that, you can add a lot of agentic infrastructure from LLM agents field, and I'll show you different examples. But before that, how can you measure? So before implementing anything, right, you want to establish a nice metric. So the first thing to do is obviously how well it drives. And there are several simulators like Carla, Nuisance, there are new upcoming nerve simulators that Nikhil was talking about. There's a high-end environment, which is simplified simulator. The second thing you want to do is to measure how well vision and language work together. And for that, there is this beautiful picture on this Drive LM GitHub that you can see where they show all sorts of data sets that test video to language conversion. Specifically, it could be VQA or explainability. Here's the BDDX data set. There is also a Lingo QA data set that Wave released already. And one specific thing that we also released is this new technique where to test how well model answers a certain question, we train yet another LLM as a judge that just predicts correctness score. Because when we started to work on VLMs, we found that typically used metrics like Meteor, Blue, and so on are not really capturing all the semantics for self-driving. They're capturing the sentence structure, but they often lose the nuanced meaning, like, okay, was the car actually left or right? Like one word can matter a lot in such scenarios. And we found it a kind of a fruitful approach where you just actually fine-tune yet another LLM to compare between VLM answer and a human answer, and then just gives you a score. And we released the paper on that, so you can read about this, and it leads to very nice correlation with humans. So another thing you want to measure, which is very non-trivial, is the whole alignment between vision, language, and action. So if you think about like three modalities, actually, so it's not only visual and language, but also action comes in, and it's all happening in a closed loop. And it's very tricky how to measure all those capabilities. But there are new benchmarks coming up. So there are at least three I listed here: LangAuto, LangPilot, and Dorothy. And some of them measure instruction following. Some of them measure reasoning in a closed loop. So you can check them out. All right. So just kind of a division of all the work that happened in LLM-based driving. The initial papers that appeared, they mainly focus on this agentic infrastructure, where originally there was no really many strong VLMs, visual language models. So people used ChatGPT using API, just trying to play with this idea of how to use language for driving. And in this picture, I'm kind of labeling in green like amount of focus or amount of research that was put into one of the aspects of that driving. So you can see that in those papers, majority of work was put in a agentic kind of LLM text-based infrastructure. So here are some examples. This is the earliest paper I was able to find, actually. It's called Drive Like a Human. And in that paper, they use this highway environment. They take observation from different lanes, put it into text, and let ChatGPT reason about it, right? So ChatGPT can generate different discrete actions in text, and then you parse that and you put it back. And even already there, quite some time ago, actually, it was like in the summer 2023, they already did very advanced kind of reasoning techniques with memory. So you can see that, okay, so you see those two cars, and first ChatGPT answers, okay, I want to just stop and wait for other vehicle to pass, but in reality, you can just go because there's not a gap. They implemented self-reflection where there is a human kind of correction for that reasoning, and then GPT reflects on that, saying that, okay, well, there was enough space that is added into the memories, and then later that's next time you see the same kind of situation, you use that memory, self-reflection, and so on to correct your decision and actually implement the correct driving decision. So you can see that this is very sophisticated reasoning already happening with very early ChatGPT models just using API. And a few other papers along those lines is, so for example, Agent Co-Driver. Here they added yet few more advanced features. For example, they added a module so that you can communicate with words with other vehicles, which is, again, it just takes advantage of the language being this very nice compressed medium. You can just say to everyone else saying, okay, I'm just changing lanes to the left. And other cars being also autonomous driven by LLMs can understand this and react appropriately. And you can see that there are quite many features this paper introduced. There was a memory and lifelong learning, self-reflection, verbal communication with others, and chain of thought. Yet another paper along those lines is called Language Agent. Used another technique from LLM agents, which is usage of tools. Specifically, they had several tools available to them. For example, you can get a leading object or some kind of predictions, and then take decisions based on all those tools. Use some kind of reasoning, and even use retrieval augmented generation, where you use some kind of embeddings to get the most common text descriptions of the scenarios that you have seen in the past. So next set of papers focused on kind of the right part of this diagram, where instead of focusing on agents, people focused, okay, how can you transfer action? How can you parse action from LLM into driving output? And this is a non-trivial problem. So first papers were just trying to parse very simple discrete actions. But here I just found a few more advanced papers. For example, Language MPC is the one that I quite like. Is a paper where LLM actually controls parameters of MPC controller and can take this high-level decision like tuning coefficients for MPC. And specifically, when you do this, you get those advanced features like driving style adjustment. For example, you can say in a pre-prompt that, okay, I'm an aggressive driver or I'm a conservative driver, and deciding LLM would appropriately tune the parameters of NPC and do kind of appropriate behavior. And another interesting two set of papers, Langprop, actually from Wave, from Shu, our intern, and LM Pilot, they went into another kind of approach where LLM generates code that is then executed on a closed loop simulator. So instead of generating simple decision, you generate the whole procedures, which is a very interesting idea. All right, so then after that, several VLMs appeared, and here's a small review of those papers. This is the kind of the general architecture of VLM that drives a car. So here, instead of text, you actually have vision that goes through vision token bridge, and then later goes through vision language model and some action. And in those papers, people did not really focus on this agentic infrastructure, but mainly focus on vision. So this bridge is the main kind of focus of the research in this area. So here is a few papers that I selected. First is Drive GPT-4. And here we can see this typical scheme where you take in frames, you use visual encoder, and typically what's used is clip, like everyone else. You know, people found in self-driving that, okay, well, the best visual encoder that transforms images in text is clip. Then you take that, you have a learnable projections, which generate tokens for large language model, which you can train or fine-tune with LoRa, or just freeze and just fine-tune projections. And using that, they got the state-of-the-art on BDDX. So this is where we first have seen that large language models get state-of-the-art on explainability data sets. All right, so we also at Wave had a very similar project, very similar idea, which is called Lingo 1. So we released actually an academic version of Lingo 1 in the paper Lingo QA, and architecture in that model is very similar. Also, we take images, pass it through clip, pass all that through QFormer, and have a large language model. Specifically, the best was Vicuna. With that paper, we actually released the data set, training data set. We released Lingo Judge that I mentioned before, and various just ablations of very different parameters that you can tune here. And here's the demo of Lingo 1. This is a more kind of sophisticated version, but I still can participate in a dialogue, so I can read here. So user asks, what's the weather like? And Lingo says it's rainy. Do you drive differently in rain? Yes, I need to be more cautious due to rainy conditions. How come? Due to rainy conditions, the road might be slippery and visibility might be reduced. So when will you go? I'll go once the black sedan in front me start moving. So you can see kind of scene understanding here. And then it kind of goes into this generic rant, right? So when will it stop raining? It says, I cannot predict. So is it true that it always rains in London? And it says, no, it's not true, which is actually correct. Today was a sunny day. So the next section of papers are like a set of papers that focus on perception. And in that set, people focused mainly on how can you generate not only language, but also additional perception output. And typically it would be bounding boxes or segmentations. So in that approach, those two areas where how can you put kind of vision into the language model such that they can predict bounding box segmentation are the main areas of research. And one of the most advanced one that I found actually is this paper called Embodied Understanding of Driving Scenarios. And the guys here trained on many data sets. Well, data sets included Nuisance, Waymo, Ego3D, YouTube, and so on. And it's actually quite sophisticated architecture that involves this idea of time tokens, such that a model can have temporal predictions, not only responding to what it sees now, but also predicting the future and refer what happens in the past, and also generate some perception. So here in my opinion, quite sophisticated examples of what it can do. So for example, you can ask, what's the 3D spatial location at a certain pixel 2 seconds ago? And the model correctly predicts what happened at that location, and it was a pedestrian at that location, so it identifies a pedestrian and says where he was. It can do also regular action decisions, so you can just query by a bounding box what do you need to do for that specific car, right? And it's correspondingly figures out that where this car is located and what to do with it. And it can do 2D to 3D kind of a transformation where it clearly shows that it understands 3D world. It becomes really sophisticated perception system. And another paper I wanted to highlight is called HILM-D. And the main challenge that they addressed is that in self-driving, as opposed to like many generic video understanding systems, you really want to pay attention to small objects, which are very important. And those are traffic lights and traffic signs. Those are typically quite small. They could be far away, but you want to really, you never want to ignore them. And that specific paper focused on a vision system that has 2 different branches, so with low resolution, high resolution videos, such that from really quite far away and like using just 1 pixel, they can predict that there is a red traffic light. You can see like a very small bounding box here. And hence it's a very nice solution to do this kind of detailed perception. We also at Wave played with that idea of referential segmentation, and what we did, we attached a segmentation model to Lingo 1. And this is a small demo of this. So you can see a user is asking what are you paying attention to. And the model not only responds to that, but also identifies 2 regions, A and B, as a segmentation masks, and says that I'm paying attention to drivable area and the traffic in front. And then you can ask even more stuff, and it says, okay, well, now I'm paying attention. So you can ask about objects in the world, like what are the broken white lines mean? And you've seen that it selected the lines correctly and predicted what it is. All right, but the most interesting models, in my opinion, are the models that actually can drive end-to-end in a closed loop and use visual language. And for that, just small digression is that if you think about why do we trust human drivers to drive a car? If you think, so humans are they just pass a theory driving test that takes at most 1 hour in some countries, in some countries even less. And pass a practice driving test, which also at most can last 1 hour. And if you think about it, this is way less than what we do in the self-driving companies, where we test every model orders and orders of magnitude more than 1 hour. And obviously right now VLMs can just go and pass a driving test. It's been shown a few times on the YouTube. You can check out the GPT-4 pass a driving test. So why do we trust humans? So the one thing is that humans share all common knowledge with us, right? So like other drivers share knowledge with us, so we trust them. For example, we don't allow kids to drive. But now you can see VLMs have that knowledge now, so we should kind of trust them more. Another reason that humans can explain decisions. But this is actually a bit misleading, because if you have a VLM that just explains decisions, it's not obvious that those explanations actually relate to actual action that the model took. So you just have like two robots speaking. One is driving, another one just tries to explain what's happening, but it's not clear that explanation is related to the action. So the reason we trust human explanation is that we know that it's all in the same kind of brain and same substrate, and it's all happening in a closed loop. And this is, I believe, the main kind of the ultimate system where the system can predict, explain, and so on, and drive together through the same weights, through the same network. And those are the VLM-based papers. One of the early ones is called Drive Anywhere, where researchers use the, again, very similar idea of a VLM, and well, it's mainly clip-based kind of model, but it actually was tested on a real car where the network actually predict control signals. Another very great paper along those lines is called ML Drive. I already mentioned that. So here, this is this prototypical system where you take in video, again, for the very similar clip and Q former and so on. But then also you generate tokens of actions. And then what you can do is that you can test it in a closed loop, which those guys did. So yet another innovation of this paper is that they also took LiDAR input and put that into the LLM. They use specific pre-training kind of step first to align vision and LiDAR to just get a nice visual features, and then put it into language model. So you can see people started to like test those models in a closed loop, generating actions through the same weights. Another interesting one is called ADH, and here you can so here the original idea is that there are actually two models. One is a high-level VLM that can do reasoning and has way more parameters, so it can go answer questions. But then what happens is that model modulates another low-level controller, which is also a VLM, but it's way smaller, so it can go and drive a car. So specifically here, it predicts waypoints. So it's like hierarchical architecture, but also can drive closed loop. And we at Wave recently released this Lingo 2 model, and this is the first language model that ever drove on just real public streets, right? So it's been tested in the real world. You can see the text it generates is kind of explanation of its actions. And in green, you can see the trajectory that it takes. So it's first a VLM that can explain itself, but also take action through the same weights, right? And this is hopefully leads to better alignment and explainability. All right, this is kind of very high-level training recipe of Lingo 2. So first we pre-train a vision model, then we align language and vision, and later, obviously, we add action through our own kind of driving processes, and we get a full model that can do language, obviously vision, and then driving. And the last paper, but not least, just very fresh. So recently, our intern Catherine released a model called Carlava, and we got the first place on a Carl Autonomous Driving Challenge with that. And this is also based on a language model, specifically Llama. And this is a small demo of that. So you can see this is also a model that can go and drive a car, just goes for some tricky situations. And there are two flavors of that model. One doesn't use language, one does. And this is the one where it generates language. so you can see it auto-regressively generates trajectory and then language token. So you can see highlighted explanations here. Just scroll down a little bit. Oops. Yeah, so you can see pedestrian, it highlights the pedestrian. And then it correctly identifies construction sign with explanations below that it's going to go and go around it. So you can see the demo later. All right, so as a conclusion, so first of all, there are a lot of unsolved problems. So this is all work in progress, very fresh field, LLMs and autonomous driving. There are measurements problems. We don't quite know how to robustly measure vision, language, action alignment. There's not a lot of high quality vision text action data. It's mainly auto labels, not human labeled yet. I'm not aware of like any big human label data set. So Clip is not really great for self-driving. One of the lessons is that we would love to have one of the lessons of our team is that it would be great to have a model that is really good at spatial reasoning, whereas Clip is more like sometimes acts as a bag of words, right? So we just want something spatial and can reason in language. Also, large language model is not super efficient, right? So you don't want to run like 70 billion parameter model on a car. So there's a lot of work needed for efficient inference. And in general, there is not yet like one big model that has agentic features and can drive end to end. This is like a small table I made. So in green, it means that some feature is implemented, and you can see there is no single column that is all green. Specifically, features are closed loop evaluation, can run a real car, can participate in a dialogue, referential perception, agent capabilities. So far yet there is no single paper or work that can cover everything and be like this holy grail of LLM, visual LLM in a self-driving that can do all of that together. All right, and just final thoughts, like just hand wave argument kind of for LLMs and self-driving. So before so there's always this question in the field, like, do you need AGI for self-driving, right? And there were always two camps, and there was like really no winner, right? Some people say like, okay, you don't really need any human level intellect to drive. It's too far away anyway. We can't afford it. And maybe self-driving is like a narrow task, right? So it was called narrow AI, right? But people who argued for AGI, the good arguments are that roads are actually designed for humans. So it's better to have human intellect. And another good argument is if you do solve AGI, then driving is like an easy problem. And if you think about like a lot of edge cases that happens during driving, you know that humans actually they use all the intelligence they have sometimes, right? Sometimes people drive reactively, but sometimes you need logic and so on. But after 2023, some of the arguments on a camp without AGI kind of went away, right? So first of all, AGI is becomes like closer and closer. And we have a lot of released pre-trained models, so you don't have to solve it yourself, right? So hence, I think it's a good idea to like jump on this train and claim that yeah, we actually do need AGI for self-driving. So let's try use this technology VLMs, which is kind of the closest we have for self-driving. Yeah, thank you. That's the end of my talk.
Hello, can you hear me now?
Yeah. Mm-hmm.
Okay, so I would like to know regarding the LLMs. So as you know, LLMs hallucinate. So when we use them for reasoning and based on that, we are trying to utilize for like we are taking that as a prompts for driving capabilities. So what do you think about the safety implications of that if they, let's say, hallucinate about something that can actually make the driving maybe unsafe for humans. So what do you think about that? Yeah, thank you.
Yeah. Yeah, so as I said, mixing LLMs and in autonomous driving is a extremely, early field of research. So we kind of don't know the answers on those questions. Everyone in the world tries to reduce hallucinations. So one cool thing about using pre-trained LLMs is that you kind of piggyback on a lot of other researchers trying to solve problems for you, right? So instead of trying to solve it yourself, you know that, okay, a lot of people, working to make LLMs hallucinate less, right? And so another kind of view is that no matter what, you want to have really robust testing infrastructure for all your self-driving models, right? So we at the companies, since we're doing end-to-end driving, we have to have very robust testing infrastructure, off-road evaluation, like in neural simulators, and on-road evaluation, so on. And no matter what, whether we use reasoning or don't, we have to have that done, and hopefully that catches all the regressions possible, right? So we're really investing into all sorts of evaluations, but as I mentioned, evaluations is not really yet a solved problem specifically for LLM. So there's not much work done on like reasoning. For example, hallucinations and self-driving, I'm not aware of any good benchmark yet. So yeah, the single, it's not a great answer, but yeah, it's a kind of work in progress.
Yeah, thanks for the talk. So actually, I have a question. So nowadays there is another like route way is just using the word model things, right? So in terms of this VLM strategies, compared with the word model strategy, what do you think? Which one? Yeah.
Yeah. So well, we are pursuing both of them at the company, and obviously, even Gianluca presented this paper where people started mixing those, right? Where a single model can generate language and video at the same time. So there are ideas of putting it together and try to take advantage of both models, right? So there are papers, I forgot already the name of it, claiming, okay, you can do reasoning in the visual space, right? The fact that you can predict the future and you can predict different futures, this is how Monte Carlo research even right, works, is that by predicting multiple futures and figuring out what's the best one, it's also certain, well, it's a reasoning, right? It's a planning and reasoning kind of paradigm. So there's definitely a lot of ideas how to mix them together, and I don't think they are, they're complementary, right? I think there's definitely a lot of research to be done. How do you do visual reasoning and language reasoning at the same time? And in fact, this is what humans do, right? So humans can imagine futures, but also humans can reason about future in words, right? And all of that obviously is beneficial.
Thank you for the great presentation. I have one question. So the chat box of the LLM to respond to the user to indicate how does the vehicle thinking is pretty interesting idea. Just thinking about instead of just responding to the user, will it possible that the user prompting will potentially affect the driving of the vehicle? So for example, if the user prefer driving in the highway instead of local road, prefer to drive in the middle of the lane instead of the carpool lane and the rightmost lane, would that make it possible to interact between the user and the vehicle itself?
Yeah. And so I'm going to publish the slides, and there is a list of papers, and some of them actually explored that exact idea. Not exactly the example that you're saying, but the idea of instruction following, idea of interaction with users, specifically those papers that focused on LLM part, not the VLM part, because unfortunately, still we still don't have good papers on VLM agents, right? On visual agents, but there are papers exploring exactly those ideas. Yeah, and answer is yeah, it's possible. People demonstrated that, and yeah, hopefully that's the future, right? So you can change the style of driving. Say, okay, I want to drive more maybe safely or aggressively or stuff like this, right? You can even instruct, okay, you have to go left or right, and all permutations of that.
Thank you so much. I'm really looking forward to the papers. Thank you.
All right, let's thank again Oleg for the great chat and talk. And for the last talk, we have Alahe, who is head of AI research at Wave. She will talk about the future direction of end-to-end autonomous driving. Alahe, it's all yours.
Can you hear me?
Yeah.
Okay, great. And can you see the slides? Because I can't see this.
Yes.
Okay, great. That's amazing. Welcome everybody to this final session. It's amazing you made it. My name is Elahe and I'm head of AI research at Wave. And I'm trying with this last session first recap everything that was discussed today in very briefly, and then discuss also very briefly at the end the advancement, challenges, and the future direction for the end-to-end autonomous driving systems. The agenda would be first, we will go through why end-to-end compared to modular systems, and then what was the advanced and technology up to here. We will go through the simulators, world modeling, language for self-driving, and at the end, we will discuss the directions and the challenges for the future research. Some of those will include like data scale, safety, memory efficiency, and so on. The first question is the why end-to-end autonomous driving. This diagram was shown a few times already today. I go very briefly into that. The traditional autonomous driving, which also we know them as a modular approach or AV 1.0, they are combined of multiple modules. They have perception, planning, prediction, localization, and many more modules that they are all working stack back to back with the hand engineering systems to make the autonomous driving work. These systems already, they are very complex. Each are coming with more, like each component comes with its own error that end up to have a cumulative error or compound error effect at the end of this decision-making process, which leading to be a non-scalable solution, and it's constrained with the hand engineering rules, and their reliance heavily on the HD maps make them also reduces their applications, because many roads are changing over the times. Every single day, the roads, even in the urban area in the cities, are changing, and then new rules are new roads are added, and then you are driving out of roads, not everywhere, that very frequently the maps are getting updated based on that. In AV 1.0, as I mentioned already, the individuals modules are coming with the errors from individuals modules are compounded over the time, creating significant system errors. And also the safety of these systems at unknown situations still is at question. Although later we will come back to these concepts that maybe it's in the community, it's more accepted that they are more interpretable because you know what should be the output of each module, but how the modules all together end up to interact with the world is still unknown, and the safety scenarios are limited there. In contracts, we have end-to-end AI systems or AV 2.0 that we are combining all these modules into one neural networks. And then we let the system to decide and optimize for these errors that every individual modules in the AV 1.0 has to work with. This approach eliminates the need for intermediate representations and allowing for direct optimization for the end results, as I already mentioned, and it's more scalable. Something that we haven't touched it yet, these both systems, they need safety subsystems because of regulations and also the public trust that later at the end of the session, we will go through that. Why end-to-end systems? These systems are highly portable because they use uniform computation structure. They can easily adapt to new kind of hardware settings and also vehicles, and simplifies development with fewer modules, which is a huge advantage, and achieves better performance compared to these traditional human-coded systems or rule-based design systems. This makes them a compelling choice for future autonomous driving solutions, and that's why the whole tutorial was around the end-to-end systems. One very important thing we need to remember is that perception is crucial for our decision making, but in the real world and real challenge, it lies in the decision making process itself. Embodied AI must generalize to new unseen situations and adapt to different vehicle types and geographies. This is what it's coming at the decision-making process. Although the system can realize the traffic signs and many other maybe objects, but still the decision-making, how to interact with this dynamic world and evolving world around it, that's the major challenge. This challenge itself requires robust decision-making capabilities that go beyond a simple environment perception. This coming from a very nice survey paper that today was briefly discussed. I want to touch it back because we can, after establishing, okay, we have AV 1.0 and 2.0, and 2.0 comes with many more advantages over the first modular systems approaches, the conventional approaches. Now how we can test and verify and train these systems. We can use real world data, we can test them or even use the closed loop data, and we can do this verification and validation over open loop. There are so many challenges, some of them we already mentioned, it was already touched. One thing that I want to specify here is that interpretability is different than explainability, and still it's a question that do we need to that the systems to be interpretable, or we want them to be just explainable. Interpretability maybe goes more at the like the level or modules, more than just the whole process if the system make any decision and can explain the root cause of that decision. And some of the future trends that it's like zero shot or few shot learning. Why we need that? Because every day we might come with a very new scene and scenario that nothing similar to that was already included in the data base that the models were trained. And this few shot learnings are very useful. Imagine you are driving in Europe and then you go to USA, or in UK and then USA, or the other way around. You can quickly adapt yourself from right-hand side driving to the left-hand side driving. And these capabilities are coming with the few-shot learning or zero-shot learning, or even the traffic signs from one country to the other country slightly might change. And if you just train your models to be to learn based on this memorization or recognition of the traffic signs perception modules that is coming with AV 1.0, then this might be very limiting our driving system to just one country. Let's now recap some of the recent advances and technology in the field that was already discussed, and this includes generative models for trajectory prediction, data-centric approaches for continuous improvement, and the integration of language models into the driving systems. The generative models, they are coming with many advantages. This includes text and video models trained on supervised video and at the internet scale, text data. Very huge amount of knowledge is already there available. And this is coming to us how to use them and leverage this knowledge from the text into our decision-making process. These models show emergent reasoning capabilities and enhanced planning in the combination with the word models and the video generations. High fidelity simulators are crucial. Why they are crucial for different aspects. It's coming from the training, generating the edge cases, which is very hard and scarce to capture in the real world, or sometimes they are very dangerous and we cannot even try to capture those data. We should avoid as much as possible. And in other cases, because they are so rare, then there is almost impossible to drive, or you need to drive millions of kilometers to capture these scenarios. And then the simulation comes handy to generate for the training purposes, also for evaluation. And it goes from open loop that has the model output doesn't interact with the simulator and doesn't impact the states of the simulator, to the closed loop, which the model interacts with the simulator and the state is changing over the time based on the action. A word model was, Gianluca did a great job, went through the many papers. I'm going back to a basic definition of it. A word model is generative models that predict future states based on the current state and the action. And these models are valuable for dynamic and reactive simulations, something that at Wave we are using at the moment. And also they are very useful for what if, creating this counterfactual experimentation, something that they are very useful again for the safety scenarios, for checking if the action and language are already grounded, and many other use cases are coming with the counterfactuals. And then the model-based reinforcement learning and search-based planning. These models are key to advancing autonomous driving technology, and their use cases is going beyond that. This was already also shown, but for re-emphasis on how the field is growing so fast from within a year almost, how many papers are coming in this field, and still there are so much room for improvement. And I hope this tutorial is just encouraging you to pick some of the topics, some of the challenges and unresolved problems, and start working on them. The other concept that it was just before this session was discussed is the multimodality integration into the driving system. One of these very useful modalities is the language because it comes with a huge knowledge which we can use the internet scale data for acquiring that knowledge. And now we have vision, language, action models that they are interacting and they can use for different purposes for making the system more safer, more trustable because they can explain their actions and also to making more informed decision making and also coming with zero shot inference. Explainability was one of the reasons behind the language models. There are other opportunities also coming with the language in autonomous driving. One of them is the intelligence, this huge knowledge that comes. And the other one is the trust and safety. If the model can reason behind its action, not just taking an action based on some perception and planning, but can reason like what's going on around me in the environment and how every other agent around me is going to interact with me and react even maybe to my action, then this reasoning, if it's there, then the public can trust such a model more than the others. This is a great summary of the differentiation between the AV 1.0 and AV 2.0. The AV 1.0 is rule-based. It's coming with many modules for perception, prediction, planning, and also the reliance on HT maps. They are not robust to OOD, and also they are not scalable. And because of HT maps, their application is very limited to the routes that already we have the HD maps for. The AV 2.0 has also data-driven approach and principle-based approach. The difference is that for principled approach, we have multimodality, and then we use word models and so on. This approach comes with the knowledge from the whole internet. It's a real world, and also the reasoning behind interaction with the real world physics and the prediction. It enables zero-shot generalization, and we can make use of chain of thought reasoning. And Wave, it's already pioneered in using the principle-based approaches. Many of our papers and blog posts is coming, such as Lingo 2, that is already in the same era. Now looking ahead, we already have many challenges that we have had some advancement in those, although none of them are fully solved. But there are coming with a few more challenges. This includes diverse real-world scenario, managing vast data scales that will come or we need, ensuring safety, making quick decisions, and optimizing efficiency. Unique challenges that we are in the real-world deployment for autonomous driving facing at this time, they include processing massive data. This massive data could be handling diverse and unpredictable, like we don't know how much more data we need to capture to handle those. And at the same time, every single day and every deployment that we have on the road, it brings more data, and how we are going to train, how we are going to manage, and how we are going to update the models based on this new data, that's also another aspect. Therefore, there are two different directions with handling huge data sets. Data scales, also the safety concerns that I will discuss briefly, optimization and the decision making. These roads and the interacting with the all dynamic agents in the road, even the static object like the traffic signs. They are static traffic lights, but they are changing in a fraction of time. And then the system needs also to interact in a fraction of second or even less than that to be in a safe condition. We need a lot of data. Why? Because every single day we might come with a novel combinations, such as this one that it acts like a mirror that is showing instead of looking like a truck or another vehicle, it could act as a mirror, or a rare object on the road. It could be any animal or any unknown even object. And then people are in that area creative. They can wear a stop sign or any other traffic signs, or they can dress up like a cone. And then this might be very confusing for the systems that only based on the perception, and planning is only coming from the perception-based knowledge, not a more reasoning and decision-making process that it's beyond that. There is a very big challenge with AV 2.0 is that the explainability. It's such a black box, but in general, all deep neural networks are a black box. There are millions of parameters, and then explainability of these systems are really hard. Planning and predictions also the networks that we are training right now, they are scaled poorly with respect to the input-output temporal length. The systems, they don't have a memory. How we can
We
add
have
memory
a technical issue again.
Okay.
So we can't hear you now.
Okay.
But it is resumed. Okay.
Okay, great. Yeah, one of the other things is that with the input-output temporal lengths, the networks, they don't scale or scale very poorly. We need a memory. How to add memory to the systems. This is not only for end-to-end system, it's for even the modular systems. We have this problem. How to add common sense reasoning because of all these unpredictable scenarios that we might face, and how to add change of rules or add edge case without retraining everything from scratch. This slide also was shown today, and this is very useful because when we are dealing with edge cases, we need way more data to collect than to capture any of those rare cases. But can we, with the generative models, bridge this gap with what we need for the training and what we can capture in the real world scenarios? This is another area of the research that could come very handy. But at the moment, still all this simulation-based training, at least, they are suffering from the sim to real gap that is there. Memory was already mentioned. We as a human, we have, it's coming from Daniel Kahneman, this hypothesis that brain is involved through the time, and we are using two subsystems of the memory. One of them is called system one, is they're responsible for 95% of our decision-making, reasoning, and interaction with the world. This 95 is on autopilot and doesn't need that much reasoning in the brain to make any decision. But system two is rational thinking. It's much slower in the time scale, and also it's more cautious. We need to make reasoning more, maybe level of reasoning to make any action. And it's a more cautious way of decision making. But why we need memory systems is crucial for handling this long context, the temporal context that we already mentioned for the scenarios that is needed. It's essential for reasoning and planning in the complex scenario, especially with handling the edge cases, long tail scenarios, and enables continual adaptation to this new knowledge that every single day the data are collected from the roads. As I mentioned, if we collect every single day, do we need to retrain everything from scratch? Because adding this new knowledge, it's coming with other kind of, if we don't retrain or we don't train partially on the previously seen data, it comes with many more challenges like catastrophic forgetting that neural networks are suffering from. And then if we want to get closer to AGM, that one of the aspects is learning how to learn, we need this memory system to deal with those situations. The other very important gap that already exists with all this advancement in the field that we have with the large language models, with the word models, and so on, more larger and larger models are being trained with the more number of data points. But at the end of the day, for the embodied AI, which is autonomous driving, is one of those use cases. We need to deploy on some agent that it's living in the world and interacting with with its surrounding. And for this to be more sustainable, it needs to consume less energy. But the energy doesn't come only at the inference time, even at the training, like continual learning. If we need continually update the knowledge of these agents, we need also to make them efficient. But efficiency at the model level is one of the main challenging. If we decide to go to much smaller hardware usage, then there is a huge gap at the moment. Safety and reliability of the autonomous driving in general for both AV1 and AV2 are there, and they are still unresolved. There are several unresolved challenges there. This includes managing the unpredictable nature of open world deployment, handling the massive scale of the data from multiple sensors. At any given point of time, any of these sensors can fail, and then the system needs to be reliable and be trustworthy that can decide if the rest of the sensors are enough, or at which case it can continue interacting with the world or just stop working, and ensuring utmost safety for all road users, making rapid, informed decision. Additionally, optimizing for efficiency is crucial to maintain high system performance. There is a lack of standardized and scenario databases for testing and verifying the AV systems. And the development cycle for autonomous driving in general is very slow, lengthy, and costly. And also deploying on the real world and testing for all cases is impossible because some of them are dangerous. And unclear and varying regulation across regions, going from Europe to Asia to US, there are many different rules that with different policymakers and regulators are coming. And it's really hard to handle all these different safety scenarios, although there is no agreement on what is called safety and what scenarios the system needs to be tested. So there is a new era of research that it's a still open question. The driving environment's complexity means number of scenarios for autonomous is virtually infinite. And studies suggest that providing an ADS is which is 20% safer than a human driver requires over 11 billion miles, which is very huge and almost impossible to capture for very near future, and training our models and testing them. However, simply driving many miles is insufficient because a diverse range of scenario must be encountered to ensure safety. The key challenge lies in finding the right scenario that represent the ODD of the autonomous driving system, determining if enough scenarios have been identified to guarantee system safety, considering their probability of occurrence. And challenges include assessing the safety risk associated with each of these scenarios. And then after defining all these things, then we need to define what does it mean a good behavior or pass-fail criteria for autonomous driving in given scenario. Therefore, this safety is an open field, and also there is no consciousness over that, and it needs more attention of the research community. Okay, I hope you enjoyed the tutorial and it was useful, giving you some just hint what has been done and where you can find those papers, and what is a still open question, unresolved direction and challenges at the moment, and how we can tackle them. We are hiring at Wave, and we are working on all aspects from simulation to word modeling, language for driving, efficient AI, and also the multiple memory systems, different architecture-based, very advanced and very novel. And if you are interested of any of these areas, we are hiring in London, in Silicon Valley and Vancouver, our new science office. Please go and check our website and also come and meet our team at the booth.
Hi, Elahe. Not sure if you can see me, but this is Gijs, your colleague from TU Eindhoven. Thanks a lot for your great presentation. I have one question. If you look at the human brain, it has some modularity. And so you have parts of the brain that deal with very quick visual reflexes to stay safe. And you have parts of the brain that deal more with high-level reasoning. Now, in this era of end-to-end autonomous driving, do you think that there will be some modularity? Let's say a system of networks that can be trained end-to-end, but there is still modularity? Or do you think it will in the end be just one big transformer or whatever architecture?
Hi, Gijs. Thank you for the question. Yes, brain also has some subsystems, but none of these subsystems are trained individually and in isolation with the rest of the brain. That's some differences that we are seeing with the AV 1.0. But AV 2.0 could be subsystems of different modules that also it's called AV 1.5 even sometimes, that still we think, okay, perception and everything should be trained back to back and in an end-to-end kind of manner, but still we can have this subsystem. But AV 2.0, what we are hoping or what we believe is that there is emerging subnetworks that maybe is interacting with the world. Some of those subsystems, maybe lower layers, are responsible for perception, but we are not distinguished at what level this emerging of the perception should stop and the rest for the planning should start and so on.
Yeah, okay, clear. Thank you for your answer.
All right, let's thank again his great talk. And yeah, this is the end of the tutorial, and we will release a full recording on our website. So please check our website later. And we also have a booth at 1712. So if you want to talk to our engineer and the scientists, please come to our booth. All right, thank you so much for staying so late for the video. Thank you very much.
Thanks. Thank you, Long.
Thank you. Hey, great talk.